Of all the elements in the periodic table, there is one that doesn't get nearly enough attention. It's not carbon, the backbone of organic chemistry, celebrated in countless documentaries and textbooks as the element of life. It's not oxygen, the gas we breathe and the component of water that covers most of our planet. It's not even hydrogen, the most abundant element in the universe, the fuel that powers every star in the sky. No, the element I'm talking about is far less glamorous, far less discussed, and yet without it, you wouldn't be watching this video. Without it, there would be no videos to watch, no eyes to see them, no brains to process them. Without this one element, life as we know it simply could not exist. That element is phosphorus. And here's the thing that should keep you up at night. The universe is running out of its ability to make more. This isn't some far future hypothetical scenario relegated to the heat death of the cosmos. The decline has already begun. In fact, it began billions of years ago. We are living in the long, slow twilight of phosphorus production, and the implications for life throughout the universe are profound. But before we can understand why the cosmos is losing its capacity to create this essential ingredient, we first need to understand what makes phosphorus so irreplaceable in the first place. We need to understand why, of all the elements life could have chosen to build its most critical machinery, it settled on one of the rarest options available. And we need to understand what this means for the prospects of life emerging anywhere else in the universe, or ever emerging again. Let's start with something you probably learned in high school biology but may have forgotten: the structure of DNA. Deoxyribonucleic acid is the molecule that stores the genetic instructions for building and maintaining every living organism on Earth. It's the blueprint of life, the code that gets passed from the parent to offspring, the reason you have your mother's eyes or your father's nose. DNA is often described as a double helix, two strands twisted around each other like a spiral staircase. The steps of that staircase are made of base pairs, the famous letters of the genetic code: adenine paired with thymine, guanine paired with cytosine. These bases get most of the attention because they carry the actual genetic information. But here's what often gets overlooked. Those bases would be useless without something to hold them together. The handrails of the spiral staircase, the structural backbone that connects one base to the next, is made of alternating sugar and phosphate groups. Phosphate, as the name suggests, contains phosphorus. Every single link in the chain of your DNA, every connection between one genetic letter and the next, depends on phosphorus. Without it, the double helix falls apart. The genetic code becomes meaningless, scattered letters with nothing to bind them into words, sentences, or instructions. This isn't a minor role. This isn't phosphorus making a cameo appearance in the chemistry of life. This is phosphorus playing one of the lead roles, appearing in every scene, essential to the entire plot. But DNA is just the beginning. Consider RNA, the molecule that reads the genetic code and translates it into proteins. RNA has the same phosphate backbone as DNA. Consider ATP, adenosine triphosphate, which is universally recognized as the energy currency of life. Every time a cell needs to do anything, whether it's contracting a muscle, firing a neuron, synthesizing a protein, or dividing into two daughter cells, it pays for that work with ATP. And what do you find at the core of ATP? 3 phosphate groups linked together in a chain that stores chemical energy like a compressed spring. When one of those phosphate groups is released, energy is liberated, and the cell can use that energy to power whatever process it needs. This happens billions of times per second in your body. Right now, as you read these words, countless ATP molecules are being broken down and rebuilt in your cells, each transaction requiring phosphorus. Without phosphorus, there is no ATP. Without ATP, there is no cellular energy. Without cellular energy, there is no life. We're still not done. Consider the membranes that surround every cell in your body, the barriers that separate the inside from the outside, that create the compartments where biochemical reactions can occur in a controlled environment. Those membranes are made of phospholipids, molecules that have a phosphate group at one end and fatty acid chains at the other. The phosphate end is hydrophilic, meaning it's attracted to water. The fatty acid end is hydrophobic, meaning it repels water. When you put millions of these molecules together in a watery environment, they spontaneously arrange themselves into a double layer, with the hydrophilic phosphate heads facing outward toward the water and the hydrophobic tails tucked away in the middle. This is the basic structure of every cell membrane, every organelle membrane, every biological barrier that makes cellular life possible. And at the heart of it all, quite literally at the head of every phospholipid molecule, is phosphorus, DNA, RNA, ATP, cell membranes. These aren't optional features of life. These aren't one pathway among many that evolution happened to stumble upon. As far as we can tell, these are fundamental requirements for any biochemistry remotely resembling our own. And every single one of them depends on phosphorus. Now, you might be thinking that perhaps this is just Earth life being parochial, that alien life might have found workarounds, substitutes, alternative chemistries that don't require phosphorus. And that's a fair thought. After all, science fiction is full of silicon-based life forms and ammonia-breathing aliens and all manner of exotic biologies. But here's the problem. When scientists actually sit down and try to work out the chemistry, they keep running into walls. Phosphorus has a unique set of properties that make it extraordinarily difficult to replace. For one thing, phosphorus can form multiple stable bonds with oxygen, creating phosphate groups that are chemically versatile and energetically useful. For another, phosphate bonds have just the right amount of stability. They're strong enough to hold DNA together under normal conditions, but weak enough that they can be broken when necessary, allowing DNA to be read and replicated. If the bonds were too strong, the genetic code would be locked away, inaccessible. If they were too weak, DNA would fall apart at the slightest provocation. Phosphorus hits a Goldilocks zone that other elements simply don't match. Arsenic, which sits directly below phosphorus in the periodic table and shares many of its chemical properties, has sometimes been proposed as a substitute. In 2010, there was enormous excitement when NASA-funded researchers claimed to have discovered bacteria that could incorporate arsenic into their DNA in the place of phosphorus. The headlines were spectacular. Life as we don't know it, they proclaimed. A second genesis, the shadow biosphere. But when other scientists tried to replicate the findings, the results fell apart. The bacteria in question, strain GFAJ1 from California's Mono Lake, turned out to be highly resistant to arsenic, not dependent on it. They were tolerating the poison, not thriving on it. They still needed phosphorus to survive. Subsequent studies found no evidence that arsenic was being incorporated into DNA or any other essential biomolecule. The dream of arsenic-based life evaporated under scrutiny. As of today, we have no confirmed examples of any biochemistry that can function without phosphorus. Every living thing on Earth, from the smallest bacterium to the largest whale, from the oldest archaea to the youngest newborn, requires phosphorus to exist. This isn't just an observation about Earth life. It's increasingly viewed as a potential constraint on life anywhere in the universe. This brings us to a concept that astrobiologists call the phosphorus bottleneck. When scientists search for potentially habitable worlds, they typically focus on a set of criteria that have become almost cliché at this point. Is the planet in the habitable zone, that orbital sweet spot where temperatures allow liquid water to exist on the surface? Does it have an atmosphere? Is that atmosphere protective without being crushingly dense? Does the planet have a magnetic field to shield it from stellar radiation? Is there geological activity to cycle nutrients and regulate the climate? These are all important questions, and they've guided the search for extraterrestrial life for decades. But there's a growing recognition that we may have been overlooking a crucial variable. A planet could check every box on the habitability checklist. It could have perfect temperatures and abundant water, and a protective atmosphere and active geology, and yet remain forever lifeless if one ingredient is missing: phosphorus. The bottleneck isn't just about whether a planet can support life in general. It's about whether a planet has access to the specific elemental ingredients that life requires. And phosphorus, as we're about to see, is not generously distributed throughout the cosmos. Let's talk about cosmic abundance. If you were to take a census of all the atoms in the observable universe and rank them by how common they are, you'd find a very lopsided distribution. Hydrogen comes first by a landslide, accounting for roughly 73% of all ordinary matter. Helium comes second at about 25%. Together, these two elements make up approximately 98% of everything you can see in the night sky: every star, every nebula, every galaxy. The remaining 2% is divided among all the other elements, what astronomers somewhat inaccurately call metals. Within this small slice, oxygen is the most abundant, followed by carbon and neon. Nitrogen comes in around 7th place. Iron, despite being the core of our planet and the hemoglobin in our blood, ranks only around 26th in cosmic abundance. And phosphorus? Phosphorus comes in at roughly 17th on the list. That might not sound too bad until you realize what it means in actual numbers. Phosphorus is approximately 100 times less abundant than carbon. It's roughly 300 times less abundant than oxygen. It's thousands of times rarer than hydrogen. For every phosphorus atom floating through space, there are hundreds of carbon atoms, thousands of oxygen atoms, hundreds of thousands of hydrogen atoms. And yet, as we've established, life can't do without it. This is one of the great paradoxes of biochemistry. Life on Earth has built its most essential machinery, its genetic code, its energy systems, its cellular architecture, around one of the scarcest ingredients available. It's as if evolution designed a car that runs on platinum instead of gasoline. Yes, it works beautifully when you can find the fuel. But finding the fuel is the hard part. Why did life make this choice? The honest answer is that we don't fully know. Evolution doesn't plan ahead. It doesn't consider the cosmic supply chain when designing biochemical pathways. Evolution works with what's available, selecting for whatever provides a survival advantage in the here and now. Phosphorus, despite its scarcity, must have provided advantages so significant that organisms using it outcompeted those that didn't. Perhaps the alternatives were even scarcer, or less chemically suitable, or simply didn't emerge in the prebiotic soup where life first took shape. Whatever the reason, once life committed to phosphorus-based biochemistry, there was no going back. The choice was locked in billions of years ago, and every living thing since then has inherited that dependency. We are all hostages to a decision made by chemistry before biology even existed. The only way to change it would be to start over from scratch, to build a completely different kind of life from the ground up. And, as far as we know, that has never happened, not on Earth, and possibly not anywhere else in the observable universe. The scarcity of phosphorus isn't evenly distributed, by the way. When astronomers measure the chemical composition of different stars and different regions of galaxies, they find significant variations. Some stellar systems are phosphorus-rich, others are phosphorus-poor. The ratio of phosphorus to other elements, like iron, can vary by factors of 2 or 3 or even more depending on where you look. This has enormous implications for habitability. A planet forming in a phosphorus-poor region of the galaxy might be doomed from the start. Not because it lacks water or warmth, but because it lacks the raw material for building the molecules of life. Recent studies have attempted to map these variations across the Milky Way, and the results are sobering. There appear to be zones of the galaxy where phosphorus is relatively abundant, and zones where it's notably depleted. The Sun, fortunately, seems to be located in a reasonably phosphorus-rich neighborhood. Earth inherited enough phosphorus to support a biosphere. But a planet just a few hundred light-years away, orbiting a star that formed from a different cloud of gas, might not be so lucky. This raises an uncomfortable question. When we look up at the night sky and wonder about alien civilizations, when we point our telescopes at distant exoplanets and analyze their atmospheres for signs of life, are we accounting for the phosphorus factor? Are we considering the possibility that even perfect-looking worlds might be elementally impoverished? The habitable zone, as typically defined, is a geometrical concept. It's about distance from a star, about the amount of energy a planet receives, about the temperature at which water can exist as a liquid. But habitability in the true sense, the sense that matters for life, is a chemical concept. It's about having the right ingredients in the right amounts in the right places. And phosphorus is one of those right ingredients. Without it, the most Earth-like planet imaginable is just a warm, wet rock. Some researchers have proposed expanding our definition of the habitable zone to account for these chemical factors. Instead of just asking whether a planet is the right distance from its star, we should also ask whether it formed from the right material. Is there enough phosphorus in the crust for biological processes? Is there a mechanism for concentrating that phosphorus into bioavailable forms? Are there geological and hydrological cycles that can deliver phosphorus to the environments where life might emerge? These are harder questions to answer, especially from light years away. We can detect water in the atmospheres of exoplanets. We can measure temperature and pressure and the presence of certain gases. But measuring the phosphorus content of a distant planet's crust is currently beyond our capabilities. We're flying blind on one of the most important variables in the equation of life. Let's pause here and consider something profound. The 6 elements most essential to life, carbon, hydrogen, nitrogen, oxygen, phosphorus, and sulfur, are sometimes abbreviated as SHNOPS. These are the atoms that make up the overwhelming majority of every living thing on Earth. 5 of them are cosmically abundant, readily available, easy to come by in almost any stellar system. Hydrogen is literally the most common element in existence. Oxygen and carbon are produced in enormous quantities by ordinary stellar processes. Nitrogen is not far behind. Even sulfur, while less common, is plentiful enough that it rarely poses a supply problem. But phosphorus is the outlier. phosphorus is the weak link. Phosphorus is the bottleneck through which all of life must pass. If life were a recipe, phosphorus would be the one exotic spice that you can't substitute, can't do without, and can't easily find at your local grocery store. Everything else is in the pantry. Phosphorus requires a special trip to a specialty supplier, and that supplier is running low on stock. This brings us to the central question of this documentary. Where does phosphorus come from? If it's so rare and so essential, how does the universe make it? The answer takes us deep into the hearts of stars, into nuclear furnaces where temperatures reach billions of degrees, into cataclysmic explosions that briefly outshine entire galaxies. Phosphorus is not a primordial element. It did not exist in the first moments after the Big Bang. Unlike hydrogen and helium, which were forged in the initial fireball of creation, phosphorus had to wait. It had to be manufactured later, in a process that astronomers call stellar nucleosynthesis. And the factories that produce phosphorus are not ordinary stars like our Sun. They are monsters, massive stellar giants that burn fast and die young, ending their lives in the most violent events the universe has ever witnessed. Understanding how these cosmic forges work and why they're becoming increasingly rare is the key to understanding why the universe is running out of phosphorus. The story of element creation is one of the most beautiful in all of science. It connects the smallest scales of physics, the subatomic realm of protons and neutrons and nuclear binding energies, to the largest scales of astronomy, the birth and death of stars, the evolution of galaxies, the history of the cosmos itself. Every atom of phosphorus in your body, every phosphate group in your DNA, every ATP molecule powering your cells right now was forged in a star that died before the sun was born. You are literally made of stardust, and not just any stardust, but a very specific, very rare kind of stardust that required extraordinary conditions to create. In the beginning, there was hydrogen. Well, almost. In the first few minutes after the Big Bang, when the universe was a seething soup of energy and particles, nuclear reactions began to occur. Protons and neutrons, freshly formed from the cooling quark-gluon plasma, began to stick together. Protons fused with neutrons to form deuterium, a heavy isotope of hydrogen. Deuterium nuclei fused with more protons and neutrons to form helium-3 and helium-4. A tiny amount of lithium was produced, and then, rather abruptly, the process stopped. The universe was expanding and cooling so rapidly that the window for nuclear fusion slammed shut within about 20 minutes of the Big Bang. There wasn't enough time or enough density to build anything heavier than lithium in any significant quantity. The universe emerged from its first hour of existence with a chemical inventory of roughly 75% hydrogen, 25% helium, a trace of lithium, and nothing else. No carbon, no oxygen, no nitrogen, no phosphorus, no elements that we would consider remotely interesting from a chemical standpoint. The periodic table, in those early moments, had only 3 entries. This is sometimes called the chemical desert of the early universe, and it poses a profound puzzle for the origin of life. If the Big Bang only produced hydrogen and helium, where did everything else come from? The answer, as we now know, is stars. Stars are nuclear furnaces that continue the work the Big Bang left unfinished. They take the primordial hydrogen and helium and transmute it into heavier elements, building up the periodic table one fusion reaction at a time. But not all stars are created equal. The Sun, our nearest star, is a modest yellow dwarf that has been steadily fusing hydrogen into helium for for about 4.6 billion years. It will continue to do so for another 5 billion or so before exhausting its hydrogen fuel. When that happens, the Sun will swell into a red giant, briefly fuse helium into carbon, and then shed its outer layers to form a beautiful planetary nebula, leaving behind a dense cinder called a white dwarf. That's it. That's the Sun's entire contribution to the cosmic element factory. Hydrogen to helium to carbon, with maybe some oxygen thrown in. The Sun will never produce nitrogen. It will never produce iron. And it will certainly never produce phosphorus. The temperatures and pressures required for those reactions are simply beyond what the Sun can achieve. To make phosphorus, you need a much bigger star. You need a stellar heavyweight, a cosmic giant with at least 8 to 10 times the mass of the Sun. Stars like this are rare. For every massive star capable of producing phosphorus, there are roughly 200 to 500 smaller stars that cannot. The universe is overwhelmingly populated by stellar runts, red dwarfs and yellow dwarfs and orange dwarfs that will live for billions or even trillions of years, but will never contribute to the heavy element inventory of the cosmos. The massive stars, the ones that matter for phosphorus production, are statistical outliers. They're the rare geniuses in a population of average students, the exceptional individuals who do all the heavy lifting while their less distinguished peers coast along. But massive stars don't just produce phosphorus. They produce a whole zoo of heavy elements through a process that resembles an onion being built from the inside out. Let me explain. A massive star begins its life just like the Sun, fusing hydrogen into helium in its core. But because it's so much more massive, it burns through its hydrogen fuel much faster. A star with 20 times the mass of the Sun will exhaust its core hydrogen supply in only about 10 million years, compared to the Sun's 10 billion. Once the hydrogen is gone, the core contracts and heats up, and a new round of fusion begins, helium fusing into carbon and oxygen. This helium-burning phase is shorter still, lasting perhaps 1 million years. When the helium is exhausted, the core contracts again, heats up further, and carbon fusion ignites. Carbon atoms smash together to produce sodium, neon, and magnesium. This phase lasts only about 1,000 years. Then neon burning begins, producing oxygen and magnesium. This lasts only about a year. Then oxygen burning begins, producing silicon and sulfur. This lasts only about 6 months. And finally, silicon burning begins, producing iron and nickel. This final phase lasts only about a day. Yes, you read that correctly, a day. A massive star spends millions of years fusing hydrogen, 1 million years fusing helium, 1,000 years fusing carbon, a year fusing neon, 6 months fusing oxygen, and 1 day fusing silicon. The pace of nuclear burning accelerates exponentially as the star races toward its demise. Each phase releases energy that supports the star against gravity, but each phase produces less energy than the one before. The star is running a losing race, burning through its fuel at an ever-increasing rate while getting less and less benefit from each reaction. It's like a gambler doubling down on every bet, winning less each time while the stakes get higher and higher. And here's where phosphorus enters the picture. Phosphorus is primarily produced during the oxygen and neon burning phases, those frantic final months and years of a massive star's life. When oxygen nuclei collide at temperatures exceeding 1.5 billion Kelvin, they produce a variety of products, including silicon, sulfur, and, yes, phosphorus. When neon nuclei collide at slightly lower temperatures, around 1.2 billion Kelvin, They also contribute to the phosphorus budget. These reactions don't happen in the core directly. By the time oxygen and neon burning are occurring, the core is already filled with heavier elements from previous burning phases. Instead, the oxygen and neon burning happens in shells surrounding the core. Each shell a thin layer of nuclear fusion wrapped around the stellar onion. The phosphorus produced in these shells remains trapped there, locked away in the star's interior, inaccessible to the rest of the universe, until the star explodes. The final stage of a massive star's life is silicon burning, and it produces iron. Iron is special because it has the most stable nucleus of any element. Fusing iron into heavier elements doesn't release energy. It requires energy. The star has reached the end of the line. It cannot produce any more fuel to support itself against gravity. Within seconds, literally seconds, the core collapses. The inner regions fall inward at a significant fraction of the speed of light, crashing together with such force that protons and electrons are squeezed into neutrons. The core becomes a neutron star, one of the densest objects in the universe. A ball of neutrons, just a few kilometers across but with more mass than the Sun. Or, if the star was massive enough, the core collapses all the way into a black hole, a region of space where gravity is so intense that nothing, not even light, can escape. The outer layers of the star, meanwhile, have a different fate. When the core collapses, it acts like a floor being suddenly removed from a tall building. The material above comes crashing down. But when it hits the incompressibly dense core, it bounces. A shock wave forms and races outward through the star, heating the outer layers to billions of degrees as it goes. This is the supernova, the explosion that marks the death of a massive star. For a few weeks, a single supernova can outshine an entire galaxy of hundreds of billions of stars. The energy released in those brief moments is almost incomprehensible, equivalent to all the energy our Sun will produce over its entire 10 billion-year lifetime. But the supernova doesn't just release energy. It also releases elements. All those layers of the stellar onion, all those shells of carbon and neon and oxygen and silicon and sulfur and phosphorus are blasted out into space. The shock wave also triggers additional nuclear reactions as it passes through the outer layers, a process called explosive nucleosynthesis that produces even more heavy elements. When the dust settles, literally, the remnants of the star spread out to form an expanding bubble of hot gas enriched with all the elements the star spent its lifetime creating. This is how phosphorus gets into space. This is how the rare ingredient becomes available for future generations of stars and planets to use. Without supernovae, all the phosphorus in the universe would remain locked away in stellar cores forever. The factories would run, but the products would never reach the market. Here's the catch. Supernovae are rare. In a galaxy the size of the Milky Way, containing somewhere between 100 billion and 400 billion stars, supernovae occur only about once or twice per century. That's it. 1 or 2 stars per century reaching the end of their lives in a blaze of glory, seeding the galaxy with heavy elements. The rest of the stars either live too long to have exploded yet, or are too small to ever explode at all. The phosphorus supply of the entire Milky Way depends on these rare, catastrophic events. And, as we'll see in later parts of this documentary, those events are becoming rarer with each passing eon. There's one more wrinkle to the phosphorus production story that's worth mentioning. In 2020, a team of astronomers using the Atacama Large Millimeter Array, or ALMA, made a groundbreaking discovery. They detected phosphorus-bearing molecules in a star-forming region called AFGL 5142, about 7,000 light-years from Earth. Specifically, they found phosphorus monoxide and phosphorus nitride, simple molecules that incorporate phosphorus atoms into larger structures. What made this discovery significant was that it allowed the astronomers to trace, for the first time, how phosphorus travels from its birthplace in a supernova to its eventual incorporation into new stellar systems. Here's what they found. The phosphorus molecules were concentrated in the walls of cavities, carved out by young, massive stars, as they blast their surroundings with powerful winds. These winds sweep up the surrounding gas and compress it, triggering the formation of simple molecules, including phosphorus compounds. As new stars and planets form from this compressed material, they inherit the phosphorus that was created in previous generations of supernovae. The cycle continues. Phosphorus forged in the death of one star becomes part of the birth of another. The element passes from stellar generation to stellar generation, each time getting mixed into new worlds, new environments, potentially new forms of life. This cosmic recycling process is beautiful, but it's not infinitely sustainable. Each generation of stars produces fewer massive members than the one before. The rate of supernovae is declining. The phosphorus supply is not being replenished as quickly as it once was. We are living in a universe that is slowly, inexorably running down its ability to produce the element that made our existence possible. The implications of this decline are the subject of the next part of our story. But before we go there, let's take a moment to appreciate where we are and what it took to get us here. Every phosphorus atom in your body has a history that stretches back billions of years. It was forged in the core of a massive star that lived fast and died young. It was blasted into space by a supernova that briefly outshone 100 billion suns. It drifted through interstellar space for millions of years, part of an expanding cloud of gas and dust. It was swept up into a new molecular cloud and compressed by the gravity of nearby stars. It became part of a swirling disk of material around our newborn sun. It accreted into planetesimals, then into planets, eventually finding its way to the third rock from the sun. It was buried in Earth's crust, uplifted by geological processes, eroded into the oceans, taken up by organisms, passed through countless generations of life, and ultimately incorporated into the particular arrangement of atoms that constitutes you. That journey took roughly 9 billion years. The universe is about 13.8 billion years old. Phosphorus has been around for most of cosmic history, but just barely. The earliest stars, the ones that formed in the first few hundred million years after the Big Bang, contained no heavy elements at all. They were made of pure hydrogen and helium, the primordial stuff left over from the Big Bang. When these first stars exploded, they seeded the cosmos with the first heavy elements, including small amounts of phosphorus. But it took multiple generations of stellar birth and death before the phosphorus abundance built up to the levels we see today. The Sun itself is a third-generation star, possibly even fourth generation, inheriting the elemental legacy of countless predecessors. We are the beneficiaries of this long chain of cosmic chemistry. We exist because massive stars died. We exist because supernovae scattered their ashes across the galaxy. We exist because the rare element phosphorus, against all odds, found its way into the planet where we evolved. This is not a story of cosmic abundance. This is a story of cosmic scarcity, of a universe that made life possible despite the odds, not because of them. Phosphorus is the limiting reagent in the chemistry of life. It is the narrow gate through which all biology must pass. And the gate is slowly closing. But here's the thing. Even on a planet as phosphorus-rich as Earth, the element is not evenly distributed. It's not freely available for the taking. Phosphorus tends to get locked up in minerals, bound into rocks, inaccessible to living organisms without some mechanism to extract and concentrate it. On the early Earth, before life emerged, phosphorus was a scarce resource in the environments where prebiotic chemistry was occurring. The famous warm little ponds that Darwin imagined as the cradles of life would have been phosphorus-limited. The primordial soup was thin on one of its most essential ingredients. Some researchers believe this posed a major obstacle to the origin of life. How do you build phosphorus-rich molecules like RNA and DNA when phosphorus is so hard to come by? Various solutions have been proposed. Perhaps lightning strikes or volcanic activity released phosphorus from rocks into soluble forms. Perhaps meteorites delivered phosphorus compounds from space, where different chemistry prevails. Perhaps there were special geological environments, like hot springs or alkaline vents, where phosphorus was more concentrated than elsewhere. The truth is, we don't know for certain how early life obtained its phosphorus. What we do know is that it found a way, and once it did, there was no going back. Life became addicted to phosphorus, and it has remained addicted for nearly 4 billion years. Today, phosphorus cycles through Earth's biosphere in a complex dance of biological and geological processes. Phosphorus weathers out of rocks, dissolves in water, gets taken up by plants and microorganisms, passes through food webs, accumulates in sediments, and eventually returns to rocks, where it's locked away again until geological uplift brings it back to the surface. This cycle operates on timescales of tens of thousands to millions of years. Unlike carbon and nitrogen, which have significant atmospheric components that speed up their cycles, phosphorus has no stable gaseous form under normal conditions. It stays in the solid and liquid phases, moving slowly from rock to water to life and back to rock. This makes phosphorus particularly susceptible to depletion. If you remove it from the cycle faster than geological processes can replace it, you run out. And that, it turns out, is exactly what we've been doing. But that's a story for a later part of this documentary when we bring the cosmic perspective back down to Earth. For now, let's leave with this thought. Phosphorus is not just rare in the universe. It's rare on Earth. It's rare in your body. It's rare everywhere life might want to emerge. It's a precious resource on every scale, from the cosmic to the personal. The next time you think about the chemistry of life, don't think about carbon. Carbon is easy. Carbon is everywhere. Think about phosphorus. Think about the element that life can't do without. The element forged in stellar explosions. The element that determines whether a planet can support biology or is just another sterile world. Think about how lucky we are to have enough of it, and how that luck might not last forever. The universe is running out of phosphorus. Not today, not tomorrow, not in our lifetimes or the lifetimes of our children. But the decline has begun. The massive stars that produce phosphorus are becoming rarer. The supernovae that distribute it are becoming less frequent. The cosmic supply chain that brought the element to Earth is slowly breaking down. In the chapters to come, we'll explore how and why this is happening, what it means for the long-term future of life in the universe, and whether there's anything that could be done about it. We'll journey into the nuclear hearts of dying stars and trace the phosphorus they produce across billions of light years and billions of years. We'll look at the current state of star formation in the cosmos and ask how much longer the element factories will keep running. And we'll return to Earth, to our own phosphorus crisis, to see how the cosmic story connects to the very practical problem of feeding 8 billion people on a planet with finite resources. But all of that begins with the basic truth we've established here. Life chose phosphorus, and phosphorus is rare. That choice shaped everything that followed. It constrained the possible locations for life in the universe. It limited the timescales over which life can emerge. It made every living thing dependent on the legacy of dead stars. We are bound to the cosmos not just by gravity or by the light we see, but by the atoms in our cells, atoms that were forged in violence and scattered in death, atoms that are becoming harder and harder for the universe to produce. This is the story of phosphorus. This is the story of life's most precarious dependency. And this is the story of how the universe is slowly closing the door on the element that made us possible. In the first moments after the Big Bang, the universe was a seething cauldron of unimaginable energy. Temperatures soared to trillions of degrees. Space itself was expanding at a furious rate. And in this primordial chaos, the first matter was being forged. But here's the thing that might surprise you. For all the violence and energy of those early moments, the Big Bang was remarkably unproductive when it came to chemistry. The entire periodic table, all 118 elements that we know today, was not created in that initial fireball. In fact, the Big Bang produced only 3 elements. Just 3. Hydrogen, helium, and a tiny trace of lithium. That's it. No carbon, no oxygen, no iron, no gold, and certainly no phosphorus. The universe emerged from its first few minutes of existence as an almost chemically barren place, a cosmos of hydrogen and helium with virtually nothing else. If you had been there to witness it, you would have seen a universe incapable of producing planets, incapable of producing chemistry, incapable of producing life. Everything interesting that exists today, every element heavier than lithium, had to be manufactured later. And the factories that would do that manufacturing had not yet been built. Let's talk about what actually happened in those first moments. The Big Bang was not an explosion in space, it was an explosion of space. The universe didn't expand into some pre-existing void. Space itself came into being and stretched outward, carrying matter and energy with it. In the first fraction of a second, temperatures were so extreme that matter as we know it couldn't exist. There were no atoms, no nuclei, not even stable protons or neutrons. There was only a soup of fundamental particles, quarks and gluons and leptons, all buzzing around in a state of unimaginable chaos. As the universe expanded, it cooled. Within about 1 microsecond, the temperature dropped enough for quarks to bind together into protons and neutrons. Within about 1 second, the temperature dropped further, and the universe entered a phase called Big Bang nucleosynthesis. This is when the first atomic nuclei were formed. The process worked like this. Protons, which are simply hydrogen nuclei, began colliding with neutrons. When a proton and a neutron stick together, they form deuterium, a heavy isotope of hydrogen. Deuterium nuclei then collided with more protons and neutrons to form helium-3 and helium-4. Some lithium-7 was also produced through slightly more complex reactions. And then, Almost as quickly as it started, the process stopped. The universe was expanding and cooling so rapidly that within about 20 minutes of the Big Bang, the density and temperature had dropped below the threshold needed for nuclear fusion. The window of opportunity slammed shut. There simply wasn't enough time to build anything heavier than lithium in significant quantities. The reactions that would produce carbon and oxygen and phosphorus require much higher densities and much longer timescales than the Big Bang could provide. The result was a universe composed of roughly 75% hydrogen by mass, 25% helium, and a trace of lithium so small it barely registers. This ratio, by the way, is one of the most powerful pieces of evidence for the Big Bang theory. When astronomers measure the abundance of hydrogen and helium in the oldest, most pristine regions of the universe, they find exactly this 75-25 split, precisely what the physics of Big Bang nucleosynthesis predicts. It's a stunning confirmation that we understand what happened in those first few minutes of cosmic history. But it also highlights a profound truth. The Big Bang gave us the raw materials for stars, but not the raw materials for life. Hydrogen and helium are not particularly interesting from a chemical standpoint. Hydrogen can form simple molecules like H2, and helium doesn't form molecules at all because its electron shell is already full. A universe of only hydrogen and helium is a universe without chemistry, without complexity, without any possibility of life as we know it. So, where did everything else come from? Where did the carbon in your cells originate? Where did the oxygen you breathe come from? Where did the iron in your blood, the calcium in your bones, the phosphorus in your DNA come from? The answer is stars. Stars are the factories that took the primordial hydrogen and helium and transmuted them into heavier elements. Stars continued the work that the Big Bang left unfinished. Over billions of years, through countless stellar generations, the periodic table was gradually filled in, element by element, fusion reaction by fusion reaction. This process is called stellar nucleosynthesis, and it is one of the most beautiful and profound discoveries in all of science. It connects us directly to the cosmos. It tells us that we are not merely in the universe, we are of the universe. The atoms in your body were forged in the cores of ancient stars that died before the sun was born. You are, quite literally, made of stardust. But not all stardust is created equal. Different elements are produced by different processes in different types of stars. And this brings us to a crucial distinction that will determine everything we discuss from here on out. The Sun, our nearest star, is what astronomers call a yellow dwarf. It has been fusing hydrogen into helium in its core for about 4.6 billion years, and will continue to do so for another 5 billion or so. The Sun is a perfectly respectable star, middle-aged and middle-sized, neither particularly large nor particularly small by stellar standards. But from the perspective of element production, the Sun is almost entirely useless. The Sun will never produce phosphorus. It will never produce iron. It will never even produce most of the elements heavier than carbon. The temperatures and pressures required for those reactions are simply beyond what the Sun can achieve. Here's why. Nuclear fusion is the process of forcing atomic nuclei together so tightly that they merge into a heavier nucleus. This is not easy. Atomic nuclei are positively charged, and positive charges repel each other. To overcome this repulsion and get the nuclei close enough to fuse, you need to slam them together at tremendous speeds, which means you need tremendous temperatures. The temperature at the core of the Sun is about 15 million Kelvin. That's hot enough to fuse hydrogen into helium, but it's nowhere near hot enough to fuse helium into carbon, let alone carbon into heavier elements. The Sun will eventually run out of hydrogen fuel in its core. When that happens, the core will contract and heat up, and helium fusion will briefly ignite. But even then, the core temperature will only reach about 100 million Kelvin, enough to fuse helium into carbon and a bit of oxygen, but no further. The Sun will die as a white dwarf, a dense stellar cinder about the size of Earth, having contributed only hydrogen, helium, carbon, and oxygen to the cosmic element inventory. No nitrogen, no silicon, no iron, and certainly no phosphorus. To make phosphorus, you need a much more massive star. You need a stellar heavyweight, a cosmic giant with at least 8 to 10 times the mass of the Sun. These massive stars live fast and die young. Because they have so much more mass, they have much stronger gravity compressing their cores. This means higher core temperatures, which means faster fusion rates, which means they burn through their fuel at a prodigious pace. A star with 20 times the mass of the Sun will exhaust its core hydrogen in only about 10 million years, compared to the Sun's 10 billion. That's a factor of 1,000 difference in lifespan. Massive stars are the mayflies of the stellar world, burning bright but briefly, cramming billions of years' worth of nuclear processing into a few million years of existence. But what they lack in longevity, they make up for in productivity. Massive stars don't stop at helium fusion. Once they've converted all the hydrogen in their cores to helium, the core contracts and heats up until helium fusion ignites. Helium nuclei, also called alpha particles, fuse together to form carbon-12. This is called the triple alpha process because it requires 3 helium nuclei to come together almost simultaneously. Once carbon is present, it can capture additional helium nuclei to form oxygen-16. So far, so similar to what will eventually happen in the Sun. But massive stars don't stop there. Once the helium is exhausted, the core contracts further, heats up further, and a new round of fusion begins. Carbon fusion ignites at temperatures around 600 million Kelvin. When 2 carbon-12 nuclei collide, they can produce a variety of products, including sodium-23, neon-20, and magnesium-24, along with some leftover protons, neutrons, and alpha particles. These byproducts then participate in additional reactions, building up an increasingly complex mixture of elements. The carbon burning phase lasts only about 1,000 years in a massive star. Then the core contracts again. The temperature rises to about 1.2 billion Kelvin, and neon fusion ignites. Neon-20 nuclei are photodisintegrated by the intense gamma radiation in the core, releasing alpha particles that are then captured by other neon nuclei to produce magnesium-24 and oxygen-16. The neon burning phase lasts only about a year. Next comes oxygen burning, at temperatures exceeding 1.5 billion Kelvin. This is where phosphorus first enters the picture in significant quantities. When 2 oxygen-16 nuclei collide, they can produce silicon-28, sulfur-32, and phosphorus-31, among other products. The exact branching ratios depend on the details of the nuclear physics, but phosphorus is definitely on the menu. Oxygen burning lasts only about 6 months in a typical massive star. Then silicon burning begins at temperatures around 2.7 billion Kelvin. Silicon nuclei are photodisintegrated and reassembled into iron group elements, primarily iron-56 and nickel-56. This final phase lasts only about a day. Yes, a single day. The star that spent millions of years fusing hydrogen, 1,000,000 years fusing helium, 1,000 years fusing carbon, a year fusing neon, and 6 months fusing oxygen, completes its silicon burning in 24 hours. The pace of nuclear evolution accelerates exponentially as the star races toward its doom. Let me paint a picture of what this star looks like at this point in its final days. If you could somehow see inside it, you would find a structure resembling an onion, with concentric shells of different composition surrounding the core. At the very center is the iron core, the end product of silicon burning. Surrounding the iron core is a shell where silicon is still fusing into iron. Outside, that is a shell where oxygen is fusing into silicon and other elements. Outside that is a neon-burning shell, then a carbon-burning shell, then a helium-burning shell, and finally, on the outermost layer, a hydrogen-burning shell. Each shell is a thin layer of nuclear fury, each one processing elements and passing the products inward or outward. The star is a cosmic onion of nuclear fire, with phosphorus being produced in the oxygen and neon-burning shells. But here's the critical point. All of this phosphorus is trapped. It's locked away inside the star, deep beneath the surface, inaccessible to the rest of the universe. If the star simply faded away and became a stellar remnant, all that phosphorus would be lost forever, locked inside a dead core where it could never participate in the chemistry of life. Fortunately, massive stars do not fade away quietly. They explode. And it is this explosion, the supernova, that liberates the phosphorus and scatters it across the galaxy. The supernova begins with the iron core. Iron is special among all the elements because it has the highest binding energy per nucleon of any nucleus. What this means is that iron is the most stable element. Fusing iron into heavier elements does not release energy, it consumes energy. Similarly, fissioning iron into lighter elements also consumes energy. Iron is the bottom of the nuclear energy valley, the end point of both fusion and fission. When the core of a massive star becomes predominantly iron, the star has reached a crisis point. It can no longer generate energy through nuclear fusion. The nuclear furnace that has supported the star against gravity for millions of years suddenly shuts off, and gravity, patient and relentless, has been waiting for this moment. The iron core collapses. This is not a gentle settling or a gradual contraction. This is a catastrophic implosion, a free fall that happens at a significant fraction of the speed of light. In less than a second, the core goes from a sphere roughly the size of Earth to a sphere about 20 kilometers across. The density becomes so extreme that protons and electrons are squeezed together to form neutrons. The core becomes a neutron star, an object so dense that a teaspoon of its material would weigh billions of tons. Alternatively, if the star was massive enough, the core collapses all the way into a black hole, a region of space where gravity is so intense that nothing can escape, not even light. The outer layers of the star, meanwhile, have been left hanging. The core that was supporting them has suddenly disappeared, collapsed to a tiny fraction of its former size. The outer layers begin to fall inward, accelerating as they go, gaining kinetic energy from the gravitational potential. But when this infalling material hits the incompressible surface of the neutron star, it bounces. A shock wave forms and begins to propagate outward through the star. This shock wave is initially not powerful enough to blow the star apart. It tends to stall partway through the outer layers. But a flood of neutrinos from the newly formed neutron star deposits additional energy into the shock wave, reviving it and driving it outward with tremendous force. The shock wave tears through the star at thousands of kilometers per second. As it passes through the various burning shells, It compresses and heats the material, triggering a final burst of nuclear reactions called explosive nucleosynthesis. This is a last gasp of element production, occurring in the brief moments when the shock wave is passing through. Additional phosphorus is produced during this phase, along with many other elements. The shock wave eventually reaches the surface of the star, and the entire outer envelope is blown off into space. This is the supernova explosion, one of the most violent events in the universe. For a few weeks, a single supernova can outshine an entire galaxy of hundreds of billions of stars. The energy released is equivalent to all the energy our Sun will produce over its entire 10 billion-year lifetime, compressed into a few seconds. And with that explosion, the elements are set free. All the carbon and oxygen and neon and magnesium and silicon and sulfur and phosphorus that the star spent its lifetime producing are now expanding outward into interstellar space. They will eventually disperse into the surrounding medium, mixing with the existing gas and dust, enriching it with heavy elements. Future generations of stars will form from this enriched material. Planets will coalesce from the debris. And if conditions are right, life may emerge on those planets, built from the very atoms that were forged in the heart of a star that died billions of years ago. This is how phosphorus gets into space. This is the only way phosphorus gets into space. There is no other significant source. Phosphorus is not produced in ordinary stars like the Sun. It is not produced in red giants or white dwarfs. It is not produced in neutron stars or black holes. It is produced almost exclusively in massive stars during their final evolutionary phases and during the supernova explosions that end their lives. The phosphorus in your body, in your DNA, in every cell of every living thing on Earth, was created in this way. It was forged in a cosmic furnace and delivered by a cosmic explosion. You carry within you the legacy of stellar death. Now let's talk about why massive stars are rare, because this is crucial to understanding the phosphorus problem. Stars do not form with a uniform distribution of masses. Instead, they follow what astronomers call the initial mass function, or IMF. The IMF describes how many stars of each mass are born from a given cloud of gas, and the shape of the IMF is dramatically skewed toward low-mass stars. For every massive star born with 10 or more times the mass of the Sun, there are roughly 200 to 500 stars born with less than half the Sun's mass. The stellar population is dominated by red dwarfs, small, cool, dim stars that can live for trillions of years but will never produce anything heavier than helium. These red dwarfs are the cosmic majority, the silent masses that outnumber their more luminous siblings by orders of magnitude. The reason for this skewed distribution is rooted in the physics of star formation. Stars form when giant clouds of gas and dust collapse under their own gravity. As a cloud collapses, it fragments into smaller and smaller clumps, each of which can potentially become a star. But the fragmentation process favors small clumps over large ones. It's easier to make small things than big things when gravity is fighting against thermal pressure and turbulence. The result is that most stars end up small, and only a lucky few manage to accumulate enough mass to become the giants that can produce phosphorus. This has profound implications for the element budget of the galaxy. Phosphorus production is not just limited by the physics of nuclear reactions, it's limited by the statistics of star formation. Even in a galaxy with billions of stars, only a tiny fraction are massive enough to contribute to the phosphorus supply. And because massive stars live such short lives, they cycle through quickly. A massive star born 10 million years ago has already exploded. A massive star born today will explode 10 million years from now. The production of phosphorus is a continuous but meager process, dependent on a small and constantly changing population of stellar heavyweights. There's another factor that makes the situation even more challenging. Not all supernovae are created equal. The amount of phosphorus produced depends on the exact mass of the star, its metallicity, and the details of the explosion mechanism. Some supernovae produce more phosphorus than others. Some might produce relatively little. The yields from individual events are uncertain, and the averages are based on models that have significant error bars. When you add up all the uncertainties, the cosmic phosphorus budget becomes quite fuzzy. We know phosphorus is being produced. We know it's being distributed by supernovae. But the exact rate and the exact amount are still subject of active research. In 2020, a team of astronomers made a discovery that shed new light on this process. Using the Atacama Large Millimeter Array, or ALMA, in northern Chile, they detected phosphorus-bearing molecules in a region of active star formation called AFGL, 5A-2. This region is about 7,000 light-years from Earth, and it contains young, massive stars that are still in the process of forming. The astronomers found two specific molecules, phosphorus monoxide, or PO, and phosphorus nitride, or PN. These are simple molecules, containing just one phosphorus atom each, but their presence was significant because it showed that phosphorus from ancient supernova was being incorporated into the material from which new stars and planets were forming. But the most interesting part of the discovery was where they found these molecules. The phosphorus compounds were concentrated in the walls of cavities that had been carved out by powerful outflows from the young stars. As these protostars blast their surroundings with jets and winds, they sweep up the surrounding gas and compress it. This compression triggers chemical reactions that would not otherwise occur, forming molecules like PO and PN. The phosphorus that had been dispersed through the interstellar medium was being concentrated and processed, transformed from atomic phosphorus into molecular forms that could eventually be incorporated into planets. This was the first time astronomers had been able to trace the journey of phosphorus from its origin in a supernova to its incorporation into a new stellar system. It was a missing link in the cosmic story of this essential element, and it confirmed something that scientists had long suspected. The path from stellar death to planetary birth is not straightforward. Phosphorus doesn't just passively drift through space and end up in planets by accident. It goes through a series of transformations, being processed and reprocessed by various interstellar environments before finally being swept up into a protoplanetary disk. The ALMA observations also revealed something else important. The abundance of phosphorus molecules varied significantly across the star-forming region. Some parts had more, some parts had less. This variation reflects the inhomogeneous distribution of phosphorus in the interstellar medium, which in turn reflects the random distribution of supernova events throughout the galaxy's history. A region that happened to be near a recent supernova would be enriched in phosphorus. A region that had not experienced a nearby supernova in a long time would be relatively depleted. This brings us to a concept that has become increasingly important in astrobiology: the galactic geography of phosphorus. The distribution of phosphorus throughout the Milky Way is not uniform. Different regions of the galaxy have different phosphorus abundances, depending on their history of star formation and supernova events. Some stellar systems form from phosphorus-rich material. Others form from phosphorus-poor material, and this variation could have enormous implications for the distribution of life in the galaxy. In 2020, a study led by astronomers at the University of Geneva examined the phosphorus content of nearby stars and found significant variation. Some stars had phosphorus to iron ratios similar to the Sun. Others had ratios that were notably lower, by factors of 2 or even 3. The sample was limited, but the implications were clear. Not all stellar systems are created equal when it comes to this essential element. A planet forming around a phosphorus-poor star would inherit less phosphorus than Earth did. Such a planet might have perfect temperatures, abundant water, and a protective atmosphere, yet still be unable to support life as we know it because it lacks the key ingredient. The researchers went further and tried to identify patterns in the distribution. They found suggestive evidence that phosphorus abundance correlates with position in the galaxy, with some regions being systematically enriched or depleted relative to others. This is still an active area of research, and the data are not yet conclusive, but the trend is intriguing. It suggests that the habitability of the galaxy might be patchy, with phosphorus-rich zones where life is possible and phosphorus-poor zones where it is not. Think about what this means for the search for extraterrestrial life. When we look at exoplanets and try to assess their habitability, we typically focus on factors like distance from the star, temperature, and atmospheric composition. But we rarely consider the elemental composition of the planet's crust. We rarely ask whether there is enough phosphorus for biology to function. This is partly because measuring the phosphorus content of a planet light years away is currently impossible with our technology. We can detect water in atmospheres, we can measure temperatures and pressures, we can even identify certain gases. But measuring the abundance of a solid element buried in a planetary crust is beyond our capabilities. We are, in a sense, flying blind on one of the most important variables in the habitability equation. Some researchers have proposed using the composition of the host star as a proxy for the composition of its planets. The idea is that a star and its planets form from the same cloud of material, so they should have similar elemental abundances. If you can measure the phosphorus content of a star, you can infer something about the phosphorus content of its planets. This is a clever approach, but it has limitations. The processes that form planets can concentrate or deplete certain elements relative to the original cloud. Geological processes on the planet itself can further redistribute elements. A planet's surface phosphorus abundance might be quite different from its bulk abundance, and both might be different from the abundance in the original cloud. Still, stellar abundances provide at least some information, and they're the best proxy we have for now. The galactic geography of phosphorus also raises questions about the history of life in the universe. The Milky Way is about 13.6 billion years old, nearly as old as the universe itself. But it was not always as chemically enriched as it is today. In the early galaxy, heavy element abundances were much lower because fewer generations of massive stars had lived and died. The first stars, sometimes called population 3 stars, formed from pristine primordial gas and contained no heavy elements at all. When these stars exploded, they seeded the galaxy with the first metals. But the amounts were small. It took multiple generations of stellar birth and death before the heavy element abundances built up to anything like their current levels. This means that the early galaxy was probably a poor place for life. Even if phosphorus was being produced from the very beginning, the total amount in circulation was much less than it is today. planets forming in the early galaxy would have been phosphorus deficient compared to planets forming now. The earliest possible emergence of life might have been limited not by the availability of planets or water, but by the availability of phosphorus. This is speculative, of course. We don't know exactly how much phosphorus is needed to support life, and we don't know how efficiently early life could have scavenged the element from its environment. But it's a reasonable hypothesis that the phosphorus bottleneck was even tighter in the past than it is today. Conversely, the current era might represent a sweet spot for life in the galaxy. Enough time has passed for stellar nucleosynthesis to have enriched the interstellar medium with heavy elements. Phosphorus abundances are higher now than they've ever been. Stars forming today are inheriting a richer chemical legacy than stars that formed billions of years ago. If there is a golden age for life in the Milky Way, we might be living in it right now. But golden ages don't last forever. And, as we'll see in the next part of this documentary, the processes that have been enriching the galaxy with phosphorus are beginning to slow down. The massive stars that produce phosphorus are becoming rarer. The supernovae that distribute it are becoming less frequent. The cosmic factory is winding down. We are not just living in a special time, we may be living in the best time, the peak of phosphorus availability before a long, slow decline that will stretch across cosmic ages. Before we move on to that decline, let's take a moment to appreciate the nuclear physics that makes all of this possible. The production of phosphorus is not a single reaction. It's a network of reactions, a web of nuclear transformations that depend on specific conditions of temperature, density, and composition. Phosphorus-31, the only stable isotope of phosphorus, has 15 protons and 16 neutrons. It sits in a particular place in the chart of nuclides, surrounded by neighboring isotopes that are either radioactive or can be transformed into phosphorus through various nuclear reactions. The primary pathway to phosphorus during oxygen burning involves the collision of two oxygen-16 nuclei. When these nuclei come together at temperatures above 1.5 billion Kelvin, they can produce several different outcomes. One possibility is silicon-28 plus an alpha particle. Another is sulfur-31 plus a neutron. Yet another is phosphorus-31 plus a proton. The branching ratios between these outcomes depend on the exact conditions, but phosphorus is always one of the products. Additional phosphorus can be produced through secondary reactions, such as when silicon-30 captures a proton to become phosphorus-31, or when sulfur-32 undergoes a reaction that releases an alpha particle and produces phosphorus-31. During neon burning, phosphorus can be produced when neon-20 captures an alpha particle to become magnesium-24, which then undergoes further reactions. The neon burning phase also involves photodisintegration, where intense gamma radiation breaks apart nuclei, releasing protons, neutrons, and alpha particles that then participate in additional reactions. The nuclear landscape is complex and dynamic, with thousands of possible reactions occurring simultaneously. Modeling this accurately requires sophisticated computer codes that track the abundances of hundreds of isotopes as they change over time. Explosive nucleosynthesis during the supernova adds another layer of complexity. As the shockwave passes through the star, it heats the material to even higher temperatures than the steady-state burning phases achieved. New reaction pathways open up. Elements that were not produced during the star's lifetime can be synthesized in the brief moments of the explosion. The yields of various elements depend sensitively on the peak temperature reached by the shockwave, the duration of the high-temperature pulse, and the composition of the material being processed. Different regions of the star experience different conditions, and each region contributes its own complement of elements to the final ejecta. When astronomers try to predict how much phosphorus a supernova produces, they have to account for all of these factors. They run computer simulations of stellar evolution, following the star from its birth through all of its burning phases to its final collapse and explosion. They track the nuclear reactions at each stage, calculating the abundances of hundreds of isotopes as functions of time and position within the star. They then sum up the total mass of each element that ends up in the ejecta, the material that is actually ejected into space. These calculations are computationally expensive and subject to significant uncertainties, but they're the best tools we have for understanding where elements like phosphorus come from. The results of these calculations suggest that a typical core collapse supernova produces somewhere between 1.0 and 0.1 solar masses of phosphorus, depending on the mass of the progenitor star and other factors. That might sound like a lot, but remember that the total mass of material ejected by a supernova is typically several solar masses. Phosphorus makes up only a small fraction of the total, and not all of that phosphorus ends up in planets. Most of it disperses into the interstellar medium, where it mixes with the existing gas and only gradually gets incorporated into new stellar systems. There is also a secondary source of phosphorus that we haven't discussed yet: neutron star mergers. When two neutron stars in a binary system spiral together and collide, they produce a cataclysmic event called a kilonova. Kilonovae are responsible for producing many of the heaviest elements in the periodic table, elements like gold and platinum and uranium, through a process called rapid neutron capture, or the IR process. The IR process occurs when nuclei are bombarded by such an intense flux of neutrons that they can capture many neutrons before having a chance to decay. This builds up very heavy, neutron-rich nuclei that then decay back toward stability, producing heavy elements. Phosphorus is not typically an R process element. It's too light and doesn't have the right nuclear properties. But neutron star mergers might still contribute some phosphorus through other reaction pathways that occur during the merger. The contribution is thought to be small compared to core collapse supernovae, but it's not zero. As gravitational wave observatories continue to detect neutron star mergers and astronomers continue to study their ejecta, we may learn more about this secondary source. Another potential source is a class of supernovae known as type Ia supernovae. Unlike core collapse supernovae, which mark the death of massive stars, type Ia supernovae occur when a white dwarf in a binary system accretes mass from a companion star and exceeds the Chandrasekhar limit, the maximum mass that electron degeneracy pressure can support. The white dwarf then undergoes a thermonuclear runaway that completely destroys the star. Type Ia supernovae are famous for their use as standard candles in cosmology, but they also produce heavy elements. However, their phosphorus yields are thought to be relatively small compared to core collapse supernovae. The nuclear reactions in type Ia supernovae favor iron group elements over intermediate mass elements like phosphorus. So, when we tally up all the sources, core collapse supernovae remain the dominant producers of phosphorus in the universe. And core collapse supernovae are directly tied to the formation of massive stars. No massive stars, no core collapse supernova. No core collapse supernova, no new phosphorus. The phosphorus supply of the galaxy is controlled by a tiny minority of stars that live fast and die young. And, as we're about to see, that minority is shrinking. The story of phosphorus production is really a story about two populations, the stars that make it and the stars that don't. The stars that don't, the red dwarfs and orange dwarfs and yellow dwarfs like our Sun, vastly outnumber the stars that do. They live for billions or trillions of years, quietly fusing hydrogen into helium, never achieving the temperatures needed for advanced nuclear burning. They contribute hydrogen and helium to the cosmic element budget, and that's about it. When they die, they leave behind white dwarfs that slowly cool over cosmic timescales, contributing nothing further. The stars that do make phosphorus, the massive stars, are statistical outliers. They're the exceptional individuals, the rare giants that dominate the luminosity of galaxies, but not the number counts. For every blue supergiant lighting up a nebula, there are hundreds of dim red dwarfs hiding in the background. The massive stars burn through their fuel quickly and explode before the red dwarfs have barely gotten started. Their lives are measured in millions of years, not billions. They're transients on the cosmic stage, brief flashes of brilliance that leave lasting legacies in the form of heavy elements. This dichotomy has always existed, ever since the first stars formed. But the balance between the two populations is not fixed. It shifts over time as conditions in the galaxy change, and in particular, the rate at which massive stars form has been declining for billions of years. The golden age of massive star formation, when the galaxy was awash in cosmic giants and supernovae, were lighting up the sky on a regular basis, ended long ago. We are living in the twilight of that era, a time when massive stars are becoming increasingly rare and phosphorus production is correspondingly diminished. But that is a story for the next part of this documentary. For now, let's leave with a clear picture of where phosphorus comes from. It comes from the nuclear fires of massive stars, forged in the oxygen and neon-burning phases of their final evolution. It is liberated by supernova explosions that blast the stellar ejecta into interstellar space. It disperses through the galaxy, mixing with existing gas and dust, and eventually gets swept up into new stellar systems. It becomes part of planets and asteroids and comets, incorporated into rocks and minerals and eventually into living organisms. Every phosphorus atom in your body took this journey. Every phosphate group in your DNA carries this history. The universe did not make phosphorus easy to obtain. It buried the element deep in the hearts of rare and violent stars. It made us dependent on catastrophic explosions for our supply. It scattered the element thinly across the vastness of space. And yet, despite all these obstacles, enough phosphorus found its way to Earth to support a biosphere that has flourished for nearly 4 billion years. We are the improbable beneficiaries of cosmic violence, our existence made possible by the deaths of stars we will never know. And as we look out at the universe and wonder whether other life exists, we must keep in mind that not every corner of the cosmos has been equally blessed. The phosphorus that made us possible is not evenly distributed. Some regions have more, some have less. Some planets will inherit enough to support life. Others will not. This is the phosphorus bottleneck. It's not about whether a planet is the right temperature or has the right atmosphere. It's about whether that planet has access to the one element that life cannot do without. An element that is produced only in the most extreme stellar environments, delivered only by the most violent events, and distributed only by the random geography of cosmic history. We got lucky. Earth formed from material that had enough phosphorus to support complex chemistry. We live in a region of the galaxy where supernova enrichment has been generous. Our existence is contingent on factors that had nothing to do with us and that we could never have controlled. And that existence, as we're about to see, is also contingent on timing. The phosphorus we have is a legacy of the past. The phosphorus production rate is not what it used to be. The universe is slowly, imperceptibly, running out of the ability to make more. The factories are closing down one by one as the massive stars that run them become rarer and rarer. This is not a crisis for us, not in any immediate sense. The phosphorus already present in the galaxy will last for eons. But for life that might arise in the distant future, the prospects are grimmer. They will inherit a universe that is element poor compared to our own, a universe where the raw materials for life are harder to come by, a universe that has passed its peak and is slowly winding down. This is the story we'll continue to tell in the chapters that follow. We've seen where phosphorus comes from. Now we'll see why the supply is dwindling. We'll trace the decline of star formation across cosmic history, from the explosive youth of the early universe to the quiet senescence of the present day. We'll examine what this means for the long-term future of life, not just on Earth, but throughout the cosmos. And we'll return to our own planet, where a more immediate phosphorus crisis is unfolding, one that doesn't depend on stellar evolution but on human choices. The cosmic story and the human story are connected by this one element, this one bottleneck, this one fragile dependency that binds us to the stars. The universe is not what it used to be. I know that sounds like the opening line of a nostalgic essay about better times, but I mean it quite literally. The cosmos you see when you look up at the night sky is fundamentally different from the cosmos that existed 10 billion years ago. It's quieter now, calmer, less productive. The great engines of creation that once churned out stars at a furious pace have slowed to a crawl. The fireworks are winding down, and we are living in the long, slow aftermath of a party that peaked billions of years before Earth even existed. This is not a metaphor. This is measurable, quantifiable, scientific fact. The universe's rate of star formation has been declining for most of cosmic history. The golden age of stellar birth is behind us, and with that decline comes a corresponding decline in the production of heavy elements, including the one element that life cannot do without. The universe is running out of its ability to make phosphorus, and the decline began long before any of us were here to notice. To understand why this matters, we need to step back and look at the cosmic timeline. The universe is approximately 13.8 billion years old. That number is so large it's almost meaningless to human intuition. We struggle to comprehend thousands of years. Billions are simply beyond our grasp. But let me try to put it in perspective. If you compressed the entire history of the universe into a single calendar year, with the Big Bang occurring at midnight on January 1st, then the Sun and Earth would not form until early September. The first complex life on Earth would not appear until mid-December. Dinosaurs would rule the planet for a few days around Christmas. Humans would show up in the final minutes of December 31st. All of recorded human history, every civilization, every empire, every war and discovery and achievement would fit into the last few seconds before midnight. We are newcomers to a very old universe, and the universe was doing interesting things long before we arrived to witness them. One of the most interesting things the universe has been doing is forming stars. Stars are the fundamental building blocks of galaxies, the primary sources of light in the cosmos, and, as we've discussed extensively, the factories that produce heavy elements like phosphorus. Without star formation, the universe would be a dark and barren place, devoid of the chemical complexity needed for life. But star formation is not a constant process. It varies over time, depending on the conditions in the universe. And when astronomers look back across cosmic history, they find a striking pattern. Star formation was much more vigorous in the past than it is today. The peak of cosmic star formation occurred roughly 10 to 11 billion years ago, when the universe was only about 2 to 3 billion years old. At that time, galaxies were forming stars at rates approximately 10 times higher than they are today. The universe was ablaze with stellar birth. Young, massive stars were lighting up galaxies across the cosmos. Supernovae were exploding at a furious rate, seeding the intergalactic medium with heavy elements. It was a time of cosmic fecundity, a period when the raw materials for life were being generated at maximum capacity. And then, slowly but inexorably, the pace began to slow. The star formation rate peaked and started to decline. Galaxies began to run out of the gas they needed to form new stars. The engines of creation began to sputter. This decline has been measured by numerous independent methods. Astronomers can estimate the star formation rate of distant galaxies by measuring their ultraviolet light, which is dominated by young, hot stars. They can measure the infrared emission from dust heated by star formation. They can count the rate of supernovae, which trace the death of massive stars, and therefore the birth of stars a few million years earlier. They can analyze the cosmic infrared background, the faint glow of heat from all the star formation in the history of the universe. All of these methods point to the same conclusion. Star formation peaked early and has been declining ever since. The numbers are sobering. At the peak, the cosmic star formation rate was roughly 0.2 solar masses per cubic megaparsec per year. Today, it's about 0.01 to 0.02 solar masses per cubic megaparsec per year. That's a decline of roughly a factor of 10 to 20 over the past 10 billion years. In more intuitive terms, the universe is currently producing stars at only about 3 to 5% of its peak rate. We are living in the twilight of star formation, a time when new stars are becoming increasingly rare compared to the cosmic heyday. But wait, you might say. We still see stars being born. We have beautiful images of stellar nurseries like the Orion Nebula and the Carina Nebula, clouds of gas and dust glowing with the light of newborn stars. Surely, star formation hasn't stopped entirely. And you'd be right. Star formation continues today, and it will continue for a long time to come. The Milky Way currently produces new stars at a rate of roughly 1 to 3 solar masses per year, depending on how you measure it. That's not nothing. But it's a far cry from what our galaxy was doing billions of years ago. And it's a far cry from what will be happening billions of years in the future. The reason for this decline is fundamentally about supply. Stars form from gas, specifically from cold, dense molecular gas that can collapse under its own gravity. In the early universe, galaxies had abundant supplies of this gas. They were actively accreting material from the intergalactic medium, growing larger and more massive over time. Gas flowed into galaxies along cosmic filaments, the gravitational highways that connect galaxies across the void. This influx of fresh gas provided the raw material for continuous star formation. But galaxies don't have infinite appetites, and the supply of intergalactic gas is not infinite either. Over time, galaxies consumed their gas reservoirs faster than they could be replenished. The cosmic web became more diffuse as the universe expanded. The flow of fresh gas into galaxies slowed to a trickle. At the same time, the gas that remained in galaxies was being converted into stars, which then locked up that material for billions of years. Some gas was ejected entirely by supernova explosions and stellar winds, blown out of galaxies into the intergalactic medium where it became too hot and diffuse to fall back in and form new stars. Some gas was consumed by supermassive black holes at the centers of galaxies, converted into energy and radiation rather than stars. The net result was a steady depletion of the cold gas reservoirs that fuel star formation. This process is sometimes called cosmic downsizing or galaxy quenching. Galaxies that were once vigorous star formers gradually became quiescent, their star formation rates dropping to near zero as they exhausted their gas supplies. The largest and most massive galaxies tended to quench first, having consumed their gas most efficiently. Smaller galaxies held on longer, their lower gravity making it easier for gas to survive the various processes that destroy it. But eventually, even the smaller galaxies began to slow down. Today, a significant fraction of all galaxies in the local universe are classified as quiescent or red and dead, their star formation having ceased or slowed to negligible levels. The Milky Way is somewhere in between. It's still forming stars, but at a modest rate compared to its youth. Our galaxy is classified as a star-forming spiral, one of the minority of large galaxies that still retains significant gas, reserves. But even the Milky Way is winding down. Studies of the gas content of our galaxy suggest that we have enough fuel to sustain current star formation rates for perhaps another few billion years, but not much longer. Eventually, even the Milky Way will run dry, and star formation will cease. But there's another factor at play here, one that makes the long-term prognosis even more dire. The universe is not just passively expanding, it's accelerating. In 1998, two independent teams of astronomers made one of the most shocking discoveries in the history of cosmology. The expansion of the universe is speeding up, not slowing down as everyone had expected. The culprit is something we call dark energy, a mysterious form of energy that permeates all of space and has a repulsive gravitational effect. We don't know what dark energy is. We don't know where it comes from. We don't know why it has the value it does. But we can measure its effects, and those effects are profound. Dark energy is causing the universe to expand at an ever-increasing rate. Galaxies that are not gravitationally bound to our local group are being carried away from us faster and faster. The cosmic web is stretching and thinning. The intergalactic filaments that once channeled gas into galaxies are becoming more tenuous. Eventually, in the far future, the universe will be so expanded and so diffuse that galaxies will become isolated islands, cut off from each other and from any external source of gas. The flow of fresh material that once sustained star formation will cease entirely. Galaxies will have only what they already possess, and when that's gone, it's gone for good. This cosmic isolation is not happening overnight. It's a gradual process that will unfold over billions of years. But the trend is clear and irreversible. The universe is becoming less hospitable to star formation with every passing eon. The conditions that allowed the cosmic star formation peak to occur 10 billion years ago will never return. We are not living through a temporary downturn that will eventually reverse. We are living in a permanent decline that will continue until the stars themselves go out. Now, let's connect this back to phosphorus. As we discussed in the previous part of this documentary, phosphorus is produced almost exclusively by massive stars during their final evolutionary phases and the supernova explosions that end their lives. The production rate of phosphorus is directly tied to the formation rate of massive stars. If massive star formation declines, phosphorus production declines with it. And massive star formation is declining even faster than overall star formation. Here's why. Remember the initial mass function, the statistical distribution that describes how many stars of each mass are born from a given cloud of gas. This distribution is heavily skewed toward low-mass stars. For every massive star that forms, hundreds of smaller stars form alongside it. But the ratio, C, is not fixed. Under certain conditions, the proportion of massive stars can be higher or lower. In the early universe, when gas was more abundant and more turbulent, conditions may have favored the formation of more massive stars than we see today. Some theoretical models suggest that the earliest generations of stars, the so-called population 3 stars that formed from pristine primordial gas, were predominantly massive, with typical masses of tens or even hundreds of solar masses. If true, this would mean the early universe was even more productive at making heavy elements than the current star formation rate alone would suggest. As the universe evolved, the conditions changed. Gas became more enriched with heavy elements from previous generations of stars. This enrichment actually made it easier for gas clouds to cool and fragment into smaller pieces, favoring the formation of lower-mass stars. The average mass of newly formed stars may have decreased over cosmic time. At the same time, the most extreme environments that gave birth to the most massive stars became rarer. Giant molecular clouds, the nurseries of the largest stars, are less common today than they were in the past. The most intense episodes of star formation, the starbursts that can produce hundreds of massive stars in quick succession, are becoming increasingly rare. The net result is that massive star formation is declining faster than overall star formation. Not only are fewer stars being born, but a smaller fraction of those stars are the giants capable of producing phosphorus. The factories are closing down, and the remaining factories are smaller and less productive. The cosmic phosphorus budget is being squeezed from both ends. Let me put some numbers on this. At the peak of cosmic star formation, the rate of core collapse supernova, the explosions that mark the death of massive stars, was roughly 10 times higher than it is today. That means the delivery rate of freshly synthesized phosphorus into the interstellar medium was also roughly 10 times higher. The universe was being enriched with heavy elements at a pace that we will never see again. Today, in a typical Milky Way-sized galaxy, a core collapse supernova occurs about once every 50 to 100 years. That's still a lot of supernovae when you add up all the galaxies in the universe, but it's a fraction of what it used to be. And the decline will continue. As star formation slows and eventually ceases, the rate of supernovae will drop in lockstep. Supernovae lag behind star formation by a few million to a few tens of millions of years, the time it takes for a massive star to live and die. So even after star formation stops entirely, there will be a brief coda of supernovae as the last generation of massive stars reaches the end of its life. But once that final generation has exploded, that's it. No more supernovae. No more phosphorus production. The cosmic element factories will have shut down permanently. What does this mean for the long-term future of life in the universe? The implications are profound, if speculative. Life as we know it requires phosphorus. If phosphorus production is declining, then the total amount of phosphorus available for life is essentially fixed. We're drawing down a savings account that is no longer receiving deposits. The phosphorus that exists today, dispersed through galaxies and incorporated into planets, is all there will ever be. Future generations of stars and planets will have to make do with whatever phosphorus has already been produced. Now, I should be clear that this is not an immediate crisis. The phosphorus that already exists in the galaxy is not going anywhere on short timescales. It cycles through the interstellar medium, gets incorporated into new stellar systems, and becomes part of new planets. This recycling can continue for a very long time. Planets that form in the next few billion years will still have access to plenty of phosphorus, inherited from the earlier, more productive epochs of cosmic history. Earth itself will remain habitable for another billion years or so, until the sun's increasing luminosity makes our planet too hot for liquid water. Whatever happens to cosmic phosphorus production is irrelevant on that timescale. But on longer timescales, the picture changes. Consider civilizations that might arise many billions of years in the future, on planets orbiting stars that haven't been born yet. Those planets will form from material that has been processed through many more generations of stellar evolution. Some of that processing will disperse and dilute the heavy elements. Some will lock them away in stellar remnants, white dwarfs and neutron stars and black holes, from which they can never be recovered. The overall concentration of phosphorus in the available material may decline over time, even as the total amount in the universe remains roughly constant. Furthermore, the stars of the future will be different from the stars of today. As star formation winds down, the stellar population will become increasingly dominated by red dwarfs. These small, cool stars are the most common type of star in the universe, accounting for roughly 3/4 of all stars in the Milky Way. They're also the longest lived. A red dwarf with about 1/10 of the Sun's mass will burn its hydrogen fuel so slowly that it can last for trillions of years, far longer than the current age of the universe. As the more massive stars exhaust their fuel and die, the red dwarfs will keep on shining, slowly but steadily, for eons to come. But here's the problem. Red dwarfs are useless for phosphorus production. They never achieve the temperatures needed to fuse elements heavier than hydrogen. They will live their immensely long lives converting hydrogen to helium and nothing else. When they finally die, in the unimaginably distant future, they will leave behind helium white dwarfs that contribute nothing to the heavy element inventory of the cosmos. The stars of the future will be long-lived but unproductive. They will shine for trillions of years, but will never forge a single atom of phosphorus. This shift in the stellar population is already underway. The massive, luminous stars that dominate our current night sky are a temporary phenomenon. They're the last vestiges of an earlier era when star formation was vigorous enough to produce a steady supply of giants. As star formation continues to decline, these giants will become rarer and rarer. The sky of the far future will be dominated by the dim red glow of countless red dwarfs, stars that are individually too faint to see with the naked eye, but that collectively provide most of the starlight in the universe. What does this mean for life? On one hand, the longevity of red dwarfs provides an enormously extended window of opportunity. A planet orbiting a red dwarf could potentially be habitable for tens of billions of years, far longer than Earth's tenure in the Sun's habitable zone. That's a lot of time for life to emerge and evolve. Some researchers have argued that most life in the universe will ultimately arise around red dwarfs, simply because those stars last so much longer than larger ones. On the other hand, red dwarf planets face significant challenges. Because red dwarfs are so dim, their habitable zones are very close in. Planets must orbit within a few million kilometers of the star to receive enough warmth for liquid water. At such close distances, planets are likely to become tidally locked, with one side permanently facing the star and the other permanently facing away. The resulting temperature extremes might make habitability difficult, although some climate models suggest that atmospheric circulation could moderate the contrast. Red dwarfs are also prone to violent flares, especially when young. These flares can strip away planetary atmospheres and bombard surfaces with harmful radiation. A planet might need a strong magnetic field and a robust atmosphere to survive in such an environment. But setting aside these challenges, there's another issue that rarely gets discussed. The chemistry of red dwarf planets may be fundamentally different from Earth's. Planets forming around red dwarfs in the far future will be inheriting material from a cosmos that has been enriched by fewer supernovae. If phosphorus production has been declining for billions of years, then the material from which those planets form may be phosphorus poor compared to the material that formed Earth. Even if those planets are the right temperature and have the right amount of water, they might lack the key ingredient for biology. This is speculative, I should emphasize. We don't have direct measurements of how phosphorus abundance varies with cosmic time. We don't know exactly how the phosphorus budget of star-forming regions will change in the future. These are predictions based on our understanding of stellar evolution and nucleosynthesis, extrapolated far beyond the range of current observations. But the underlying physics is sound. If massive stars are the primary source of phosphorus and massive star formation is declining, then phosphorus enrichment is declining too. The trend is clear, even if the exact magnitude is uncertain. Some researchers have taken these trends to their logical conclusion and asked, is there a habitability window for life in the universe? In other words, is there a finite period of cosmic history during which conditions are favorable for life, bounded on both ends by eras that are inhospitable? This is a profound question with no definitive answer, but it's worth considering what such a window might look like. At the early end, the universe was too element poor to support life. The first few 100 million years after the Big Bang were dominated by primordial hydrogen and helium. Heavy elements had not yet been synthesized in significant quantities. Any planets that somehow formed during this period, if planets could even form from such pristine material, would have lacked the chemical building blocks for biology. As the first generations of massive stars lived and died, seeding the cosmos with carbon, oxygen, phosphorus, and other essential elements, conditions gradually improved. The habitable window began to open. At the late end, the universe will be too quiet to support life, at least life as we know it. Star formation will have ceased. Supernovae will have stopped. The stellar population will consist entirely of dim, ancient red dwarfs slowly burning through the last of their hydrogen. Black holes will grow, slowly consuming the remnants of dead stars. Eventually, even the red dwarfs will exhaust their fuel, leaving behind a dark cosmos of cooling stellar cinders, wandering planets, and evaporating black holes. In this far future, energy will be scarce, heavy elements will be locked away in inaccessible remnants, and the conditions for life will no longer exist. the habitable window will have closed. Between these extremes lies the window itself, a period of perhaps a few tens of billions of years, during which the universe is both element-rich enough and energy-rich enough to support biology. We appear to be living somewhere in the middle of this window, perhaps slightly past the peak. The phosphorus abundance is higher now than it was in the early universe, thanks to billions of years of stellar nucleosynthesis. But the production rate is declining, and will continue to decline until it reaches zero. We may be living in a cosmically privileged time, an era when the conditions for life are about as good as they'll ever get. This idea, sometimes called the cosmic habitability window or the stelliferous era, has been explored by several researchers. The astrophysicist Fred Adams, for example, has written extensively about the long-term future of the universe and the phases it will pass through. He divides cosmic history into several eras: the primordial era immediately after the Big Bang, the stelliferous era when stars shine and life is possible, the degenerate era when only white dwarfs, neutron stars, and black holes remain, the black hole era when even those remnants have decayed, leaving only black holes, and the dark era when even the black holes have evaporated through Hawking radiation, leaving nothing but cold, empty space. The stelliferous era, the age of stars, is the only one that can support life as we know it, and it represents a tiny fraction of the total lifespan of the universe. How long will the stelliferous era last? That depends on how you define its end. If you define it as the time when the last star burns out, then it could last for trillions of years, thanks to the incredible longevity of red dwarfs. But if you define it as the time when new stars are still being born, when the cosmic cycle of stellar birth and death is still operating, then we're already in the later stages. Star formation has been declining for 10 billion years and will continue to decline until it stops entirely, perhaps in another 10 to 100 billion years depending on the assumptions you make. We're not at the very end, but we're past the peak. The busiest, most productive part of cosmic history is already behind us. This has implications not just for life, but for intelligence and civilization. If advanced civilizations exist elsewhere in the universe, or if they will exist in the future, they face the same constraints we do. They need heavy elements, including phosphorus, to build the molecules of life. They need energy from stars to power their metabolism and technology. They need time to evolve from simple chemistry to complex biology to intelligence. All of these requirements are best satisfied during the middle of the stelliferous era, when heavy elements are abundant, stars are plentiful, and enough time has elapsed for the necessary evolutionary processes. This leads to a speculation that I find both humbling and awe-inspiring. If the habitability window is finite, then all of the life that will ever exist in the universe, every microbe and every civilization, every mind that will ever contemplate the stars, must arise within this window. Outside of it, the universe is either too young or too old for life. The window is our collective inheritance, shared by all beings who will ever exist. We are part of a cosmic community, bounded not by space but by time, limited to this brief interlude when the conditions are right. Of course, all of this assumes that life as we know it, life based on carbon chemistry and phosphorus biochemistry, is the only kind of life possible. If other forms of life can exist, based on different elements or different energy sources, then the habitability window might be wider than I've suggested. Perhaps silicon-based life could emerge in the colder conditions of the far future. Perhaps life could persist around black holes, feeding off Hawking radiation or the rotational energy of the black hole itself. These are fun ideas to speculate about, but they remain firmly in the realm of science fiction. We have no evidence that any form of life other than biochemical life is possible. Until we do, we must assume that phosphorus is essential, and that the decline in phosphorus production has real consequences for the future of life. Let me now turn to a question that might seem strange at first. Does it matter? The timescales we're talking about are so immense, so far beyond human comprehension, that it's tempting to dismiss the whole discussion as irrelevant. Who cares what happens 1 trillion years from now? We'll be long gone by then. Our civilization, if it still exists, will have presumably found solutions to problems we can't even imagine. Why worry about the cosmic phosphorus budget when we have more immediate concerns right here on Earth? I think there are at least 2 reasons why this matters, one scientific and one philosophical. The scientific reason is that understanding the long-term evolution of the universe helps us understand our place in it. Cosmology is not just about distant galaxies and abstract timescales. It's about understanding where we came from and where we're going. The fact that we exist at all is contingent on cosmic history, on the particular sequence of events that produced the sun and the earth and the heavy elements in our bodies. By tracing that history and projecting it into the future, we gain a deeper appreciation for the conditions that made our existence possible. The philosophical reason is that it puts our existence in perspective. We are not the center of the universe, either spatially or temporally. The cosmos existed for billions of years before us, and will continue to exist for far longer after we're gone. Our moment in cosmic history, the brief instant when intelligent life emerged on a small planet orbiting an ordinary star in an unremarkable galaxy, is neither the beginning nor the end of the story. It's one chapter among many, and not even a particularly long one. This perspective can be humbling, even terrifying, but it can also be liberating. If we're not the center, if we're not the point, then perhaps we're free to make our own meaning, to find significance in the brief time we have. There's also a more practical angle to all of this, one that connects the cosmic story to events unfolding right now on Earth. As we'll see in the next and final part of this documentary, the phosphorus problem is not just a long-term cosmic issue, it's also a short-term terrestrial issue. Earth's phosphorus reserves are finite, and we're depleting them at an unsustainable rate. The same element that is becoming harder for the universe to produce is also becoming harder for us to access right here at home. The cosmic story and the human story are converging on the same bottleneck, the same precious resource, the same irreplaceable ingredient. But before we turn to Earth, let's take one more look at the stars. The decline of star formation is not a distant abstraction. It's something we can see happening in the galaxies around us. When astronomers survey the local universe, they find that many galaxies have already stopped forming stars. These quiescent galaxies are populated by old red stars, the long-lived survivors of ancient episodes of star formation. They have exhausted their gas reserves and settled into a state of dormancy. Some of them are elliptical galaxies, giant balls of stars that formed most of their stellar population billions of years ago, and have been quietly aging ever since. Others are former spirals that ran out of gas and lost the ability to form new stars in their disks. The Milky Way itself shows signs of its approaching quietude. Our galaxy has a relatively modest gas reservoir compared to its past. The rate of star formation in the Milky Way has been declining for billions of years. although it received a boost from a collision with a smaller galaxy several billion years ago. Another collision is coming. The Andromeda Galaxy is hurtling toward us at about 110 kilometers per second and will merge with the Milky Way in about 4 to 5 billion years. This merger will likely trigger a burst of star formation as the gas in both galaxies is compressed and shocked. But this burst will be temporary, a brief flare-up before both galaxies settle into a combined elliptical remnant that astronomers have nicknamed Milkomeda. After the merger, star formation will resume its decline, eventually dropping to zero as the last of the gas is consumed. The merger with Andromeda is itself a consequence of cosmic evolution. In the early universe, when galaxies were smaller and more numerous, mergers were common. Galaxy collisions drove much of the star formation activity that characterized the cosmic peak. But as the universe expands and galaxies become more widely separated, mergers become rarer. Dark energy is accelerating this separation, ensuring that galaxies that are not already gravitationally bound will never merge. The Milky Way and Andromeda happen to be close enough that gravity overcomes the cosmic expansion. But most galaxy pairs are not so lucky. They are being carried apart by the expanding universe, never to meet again. This isolation has profound consequences for the future. As galaxies become more separated, they lose access to external sources of gas. Whatever they have now is all they'll ever have. And as they consume that gas through star formation or lose it through other processes, the rate of stellar birth will continue to decline. The future universe will be populated by isolated, quiescent galaxies, each one slowly fading as its stars age and die. There will be no new stars to replace the old ones, no supernovae to forge new heavy elements, no cosmic cycle of birth and death. Just a long, slow dimming as the universe winds down toward its final state. This is the context in which we must understand the phosphorus problem. The element that makes life possible is not being replenished at the rate it once was. The factories that produce it are shutting down one by one as the massive stars that run them become rarer. The universe is transitioning from a state of active element production to a state of element conservation, where the existing inventory must be recycled and reused because no new supplies are forthcoming. We are lucky to have emerged during the productive phase of cosmic history, when phosphorus was still being made in abundance. Beings that emerge later may not be so fortunate. Is there anything that could change this trajectory? In principle, some exotic processes might produce heavy elements in the far future. Neutron star mergers, for example, continue to occur even after star formation has ceased, as binary neutron stars spiral together over millions or billions of years. These mergers produce heavy elements through the R process, although phosphorus is not a major product. Perhaps some phosphorus could be synthesized through these events, extending the cosmic production window slightly. But the amounts would be small compared to what core collapse supernovae produce, and neutron star mergers themselves will become increasingly rare as the population of neutron star binaries dwindles. Another possibility, purely speculative, is that an advanced civilization might find ways to synthesize phosphorus artificially. If you could somehow create the temperatures and densities needed for nuclear fusion, you could in principle build any element you wanted. This is far beyond our current capabilities, but it's not physically impossible. A sufficiently advanced civilization might be able to run its own nuclear furnaces, producing the elements it needs regardless of what the stars are doing. but this presupposes a level of technological advancement that we can barely imagine, let alone predict. For practical purposes, we must assume that life in the universe is dependent on stellar nucleosynthesis, and that the decline in stellar nucleosynthesis is a real constraint on the future of life. Let me close this part of the documentary with a reflection on what we've learned. The universe had a beginning, and it will have an ending of sorts. Not a dramatic bang, but a slow fade into darkness. Between the beginning and the end lies a window of habitability, a period when stars shine and heavy elements are available and life can exist. We are living in that window, somewhere past its midpoint, watching as the universe slowly transitions from its productive youth to its quiescent old age. The stars that created us are becoming rarer. The processes that made our existence possible are winding down. We are the beneficiaries of cosmic generosity, inheritors of a universe that, for a brief time in its history, was busy making the ingredients for life. This perspective changes how we should think about ourselves and our place in the cosmos. We are not just residents of a single planet, or a single solar system, or a single galaxy. We are participants in a cosmic story that has been unfolding for 13.8 billion years and will continue to unfold for trillions more. The phosphorus in our bodies connects us to that story. It was forged in stars that died before the sun was born, dispersed by explosions that lit up galaxies, gathered into the cloud that became our solar system, and eventually incorporated into the molecules that make up our cells. We carry the legacy of cosmic evolution within us. And that legacy is not infinite. It was produced during a finite window of cosmic history, a window that is slowly closing. In the next and final part of this documentary, we will bring this cosmic perspective back down to Earth. We will see how the phosphorus that stars created and supernovae dispersed ended up concentrated in the rocks and soils of our planet. We will examine the human use of phosphorus, the agricultural revolution it enabled, and the crisis we now face as we deplete a finite resource. And we will reflect on what it means to be phosphorus-dependent beings in a phosphorus-limited universe. The cosmic story and the human story are about to converge, and the implications are more immediate than you might think. We have traveled far in this documentary. We have journeyed to the nuclear hearts of dying stars, where temperatures exceed 1 billion degrees and atoms are forged in the fires of cosmic violence. We have traced the debris of ancient supernovae across thousands of light years, watching as it dispersed into the interstellar medium and eventually coalesced into new stellar systems. We have surveyed the decline of star formation across cosmic history, from the explosive youth of the early universe to the quiet senescence of the present day. We have contemplated timescales so vast they make human history seem like the blink of an eye. And now, at last, we return home. We return to Earth, to this pale blue dot orbiting an ordinary star in an unremarkable corner of the Milky Way. Because the cosmic story of phosphorus is not just an abstract tale of distant stars and deep time. It is also a very immediate story about the ground beneath your feet, the food on your plate, and the future of human civilization. The same element that the universe is slowly losing the ability to produce is also the element that we are rapidly depleting right here on our own planet. The cosmic crisis and the terrestrial crisis are converging on the same bottleneck, and the implications could not be more urgent. Let me start by bringing the cosmic perspective down to the scale of our solar system. About 4.6 billion years ago, in a relatively quiet corner of the Milky Way, a cloud of gas and dust began to collapse. This cloud was not pristine primordial material left over from the Big Bang. It had been enriched by generations of stellar nucleosynthesis, seeded with heavy elements from countless supernovae that had exploded over the preceding 9 billion years. Carbon, oxygen, nitrogen, iron, silicon, sulfur, and, yes, phosphorus were all present in this cloud, mixed in with the dominant hydrogen and helium. As the cloud collapsed, it spun faster and flattened into a disk. At the center, temperatures and pressures rose until nuclear fusion ignited, and the sun was born. In the surrounding disk, dust grains began to stick together, growing into pebbles, then boulders, then planetesimals, then protoplanets. Over millions of years, the chaos of the early solar system sorted itself out. The inner planets, Mercury, Venus, Earth, and Mars, formed close to the Sun where temperatures were too high for volatile ices to survive. The outer planets, Jupiter, Saturn, Uranus, and Neptune, formed further out where water and other ices could condense. Earth inherited a particular mix of elements from this primordial disk, a mix that was determined by the history of nucleosynthesis in our galactic neighborhood. We got a lot of iron, which sank to form our planet's core. We got a lot of silicon and oxygen, which combined to form the silicate rocks of our mantle and crust. We got moderate amounts of carbon and nitrogen, which would eventually become crucial for life. And we got a relatively small amount of phosphorus, incorporated into minerals like apatite, and distributed unevenly throughout our planet's interior and surface. Every phosphorus atom on Earth today has been here since the planet formed. There is no natural process that creates new phosphorus on Earth. There is no way to synthesize it from lighter elements without the temperatures and pressures found only in stellar cores or thermonuclear weapons. What we have is what we got, and what we got was determined by cosmic events that occurred billions of years before our planet existed. This is a profound realization. Unlike water, which cycles continuously through the atmosphere and hydrosphere, or carbon, which moves between the atmosphere, biosphere, and lithosphere on relatively short timescales, phosphorus has no significant atmospheric component. There is no gaseous form of phosphorus that exists under normal conditions on Earth's surface. Phosphorus is locked in the solid phase, bound up in rocks and minerals, and it moves through the Earth system very slowly. The phosphorus cycle operates on timescales of tens of thousands to millions of years. Phosphorus weathers out of rocks, dissolves in water, gets taken up by organisms, passes through food webs, settles into sediments, and eventually returns to rocks through geological processes like subduction and uplift. This cycle has been operating for billions of years, and it's the reason phosphorus is available to life at all. Without geological activity to bring phosphorus-bearing rocks to the surface, and without weathering to release phosphorus into bioavailable forms, life on Earth would have been severely phosphorus-limited from the start. But the natural phosphorus cycle is slow, very slow, and it operates in a kind of equilibrium, with phosphorus being released from rocks at roughly the same rate it's being locked away in sediments. This equilibrium sustained life on Earth for nearly 4 billion years. Organisms evolved to scavenge phosphorus efficiently from their environments, to recycle it through their ecosystems, to make do with what was available. The phosphorus economy of the natural world is a model of efficiency, honed by billions of years of evolution. Nothing is wasted. Everything is recycled. The phosphorus in a plant becomes the phosphorus in an herbivore becomes the phosphorus in a predator, becomes the phosphorus in a decomposer becomes the phosphorus in the soil. becomes the phosphorus in a plant again. Round and round it goes, the same atoms cycling through countless organisms over millions of years. And then humans came along and disrupted everything. The agricultural revolution, which began about 10,000 years ago, fundamentally altered humanity's relationship with the land. Instead of hunting and gathering, we began to cultivate crops and raise livestock. This allowed us to produce more food on a given area of land, which in turn allowed our populations to grow. But agriculture also began to disrupt the natural nutrient cycles. When we harvest crops and transport them to cities, we remove nutrients from the soil, including phosphorus. Those nutrients then end up in human waste, which for most of history was discharged into rivers and oceans rather than returned to farmland. Over time, agricultural soils became depleted. Farmers learned to rotate crops and let fields lie fallow to restore fertility. They learned to use manure and other organic materials to replenish nutrients. But these methods had limits, and as populations continued to grow, the demand for food began to outstrip the land's ability to provide. The crisis came to a head in the 19th century. European agriculture was reaching the limits of what natural methods could sustain. Soil exhaustion was becoming a serious problem. Scientists began to understand that plants required specific nutrients, including nitrogen, phosphorus, and potassium, and that these nutrients had to be replenished if yields were to be maintained. The search was on for new sources of fertilizer. The first major discovery was guano, the accumulated droppings of seabirds that had built up over thousands of years on islands off the coast of Peru and other locations. Guano was extraordinarily rich in nitrogen and phosphorus, and its importation to Europe and North America sparked an agricultural boom. But guano was a finite resource, and by the late 19th century, the richest deposits were being exhausted. The next solution came from phosphate rock. Geologists discovered that certain sedimentary formations contained high concentrations of phosphorus in the form of apatite and other phosphate minerals. These formations had been created millions of years ago, when phosphorus-rich sediments accumulated on ancient seafloors and were eventually lithified into rock. The largest deposits were found in Morocco, the United States, China, and a few other locations. Mining of phosphate rock began in earnest, and the phosphorus extracted from these deposits was processed into fertilizers that could be applied to agricultural soils. For the first time, humanity had access to a seemingly abundant supply of phosphorus, and agricultural productivity soared. The 20th century saw two more revolutions that transformed agriculture. The first was the Haber-Bosch process, developed in the early 1900s, which allowed nitrogen to be fixed from the atmosphere and converted into ammonia for use in fertilizers. Before Haber-Bosch, nitrogen was the limiting nutrient in most agricultural systems. The ability to synthesize nitrogen fertilizer from thin air removed that constraint virtually overnight. The second revolution was the Green Revolution of the mid-20th century, which combined high-yielding crop varieties with intensive use of fertilizers, pesticides, and irrigation to dramatically increase food production. Together, these revolutions allowed humanity to feed a population that grew from about 1.6 billion in 1900 to nearly 8 billion today. Without synthetic fertilizers, this would have been impossible. Billions of people are alive today because of nitrogen and phosphorus extracted from the air and mined from the ground. But here's the crucial difference between nitrogen and phosphorus. Nitrogen can be synthesized. The Haber-Bosch process creates nitrogen fertilizer from atmospheric nitrogen gas, which makes up 78% of the air we breathe. The supply of atmospheric nitrogen is effectively infinite. As long as we have energy to run the Haber-Bosch process, we will never run out of nitrogen fertilizer. Phosphorus is different. Phosphorus cannot be synthesized. Every atom of phosphorus that we use in fertilizer has to come from somewhere, and that somewhere is phosphate rock deposits that formed millions of years ago. These deposits are finite. They are not being replenished on any timescale relevant to human civilization. When we mine phosphate rock and spread it on our fields, we are drawing down a savings account that took geological ages to accumulate. And we are drawing it down fast. How fast? Estimates vary, but the picture is concerning no matter which numbers you use. Global phosphate rock production is currently around 220 million metric tons per year. The United States Geological Survey estimates that global reserves of phosphate rock are around 71 billion metric tons, with resources, which include less economically accessible deposits, estimated at around 300 billion metric tons. If you simply divide reserves by current production, you get about 300 years of supply. If you use the larger resource estimate, you get more like 1,000 years. These numbers might seem reassuring, but they conceal several important caveats. First, phosphate rock production is not constant. It has been growing at about 2 to 3% per year, driven by increasing demand from a growing global population and rising meat consumption, which requires more phosphorus-intensive feed crops. If production continues to grow, reserves will be exhausted much faster than the simple division suggests. Second, not all phosphate rock is created equal. The highest quality deposits, those with the highest phosphorus concentrations and the fewest contaminants, are being depleted first. What remains is increasingly lower grade, requiring more energy and processing to extract usable phosphorus. This means that even if total reserves seem adequate, the economically viable reserves may be exhausted much sooner. Third, phosphate rock deposits are geographically concentrated. About 70% of known reserves are located in Morocco and the Western Sahara, a politically sensitive region. This creates geopolitical concerns about supply security. A handful of countries control most of the world's phosphorus supply, just as a handful of countries control most of the world's oil supply. Some researchers have proposed the concept of peak phosphorus, analogous to peak oil. The idea is that phosphorus production will eventually reach a maximum and then decline as the best deposits are exhausted and extraction becomes more difficult and expensive. Estimates for when peak phosphorus might occur range widely, from the 2030s in some pessimistic scenarios to the 22nd century in more optimistic ones. The uncertainty reflects our incomplete knowledge of global phosphate reserves and the difficulty of predicting future demand. But even the most optimistic estimates agree that phosphorus is a finite resource that will eventually become scarce. The only question is when. This is a very different kind of resource crisis than what we usually think about. When we talk about running out of oil or natural gas, the concern is primarily about energy. But there are alternatives to fossil fuels: solar, wind, nuclear, hydroelectric, geothermal. These technologies can provide energy without burning carbon. The transition away from fossil fuels is difficult, but it's technologically feasible. Phosphorus is different. There is no alternative to phosphorus in agriculture. There is no substitute element that can perform the biological functions that phosphorus performs. You cannot grow crops without phosphorus. You cannot feed livestock without phosphorus. You cannot maintain the human food supply without phosphorus. The 8 billion people on this planet are utterly dependent on a finite resource that we are consuming at an unsustainable rate. Let me be clear about what this means. It does not mean that we are going to run out of phosphorus next year, or next decade, or even in this century. The crisis is not immediate in the sense that an earthquake or a pandemic is immediate, but it is coming. And unlike many other environmental challenges, this one has a hard physical limit. You cannot negotiate with phosphorus. You cannot find more of it through better exploration or more efficient extraction. Every phosphate molecule that washes off a farmer's field into a river and eventually into the ocean is a phosphate molecule that is no longer available for agriculture. Every kilogram of phosphorus that we waste is a kilogram that future generations will not have. The good news, such as it is that phosphorus doesn't actually disappear when we use it. Unlike fossil fuels, which are converted into carbon dioxide when burned, phosphorus remains phosphorus no matter what we do with it. It just moves around. The phosphorus in fertilizer becomes the phosphorus in crops, becomes the phosphorus in food, becomes the phosphorus in human bodies, becomes the phosphorus in sewage. If we could capture and recycle that phosphorus instead of letting it flow into waterways, we could dramatically extend the lifetime of our reserves. In principle, nearly 100% of phosphorus could be recycled indefinitely. In practice, we currently recover only a small fraction. Consider the path of phosphorus through a typical modern food system. A farmer applies phosphate fertilizer to a field. Some of that phosphorus is taken up by crops, but a significant fraction, often 20 to 50%, is lost to runoff and erosion, washing into streams and rivers and eventually into lakes and oceans. The phosphorus that does make it into crops is harvested and transported to food processing facilities, and then to consumers, often hundreds or thousands of kilometers away. Consumers eat the food, and the phosphorus passes through their bodies and ends up in sewage. Most sewage treatment plants are not designed to recover phosphorus. They remove it from the wastewater to prevent pollution, but the phosphorus ends up in sludge that is often landfilled or incinerated rather than returned to agricultural land. Some phosphorus does make it back to farms through organic waste and manure, but the loop is far from closed. We are running a linear phosphorus economy in a world that requires a circular one. Efforts are underway to change this. Researchers are developing technologies to recover phosphorus from sewage, animal waste, and agricultural runoff. Some wastewater treatment plants are being retrofitted to produce struvite, a phosphorus-rich mineral that can be used as fertilizer. Farmers are being encouraged to use precision agriculture techniques that apply fertilizer more efficiently, reducing waste and runoff. Governments are beginning to recognize phosphorus security as a strategic concern, comparable to energy security or water security. But progress is slow, and the scale of the challenge is enormous. Transforming the global food system to conserve phosphorus will require changes at every level, from individual farms to international trade agreements. There's another dimension to the phosphorus crisis that often gets overlooked: the environmental damage caused by phosphorus pollution. When phosphorus washes into lakes and rivers, it fertilizes aquatic ecosystems just as it fertilizes agricultural soils. This sounds like it might be a good thing, but it's not. Excess phosphorus causes algal blooms, massive growths of algae that can cover entire lakes and coastal waters. When these algae die and decompose, the process consumes oxygen, creating dead zones where fish and other aquatic life cannot survive. This phenomenon, called eutrophication, has devastated freshwater ecosystems around the world. The Gulf of Mexico has a dead zone that can exceed 20,000 square kilometers in some years, caused largely by phosphorus and nitrogen runoff from the Mississippi River basin. Lake Erie, which was nearly killed by eutrophication in the 1960s and 1970s, has seen a resurgence of algal blooms in recent decades. The Baltic Sea, the Chesapeake Bay, and countless smaller water bodies are suffering from the same problem. So we have a paradox. We are simultaneously running out of phosphorus for agriculture and polluting our waterways with too much phosphorus. The same element that is becoming scarce on our farms is becoming overabundant in our lakes and rivers. This is not really a contradiction. It's a consequence of the linear flow of phosphorus through our economy. We mine it, use it, and discard it. The farms are being depleted while the waterways are being polluted. The solution to both problems is the same. Close the loop, recycle the phosphorus, return it to the farms where it's needed instead of letting it accumulate where it causes harm. Now, let's step back and connect the terrestrial phosphorus crisis to the cosmic story we've been telling. What we're experiencing on Earth is, in a sense, a microcosm of what the universe is experiencing on a much larger scale. On Earth, we have a fixed stock of phosphorus that is being depleted by human activity faster than natural processes can replenish it. In the universe, there is a finite production capacity for phosphorus that is declining as star formation winds down. In both cases, the fundamental issue is the same. Phosphorus is not easily made, and there's only so much of it to go around. The parallel goes deeper than that. Consider how phosphorus got to Earth in the first place. It was synthesized in massive stars that lived and died before the sun was born. It was dispersed by supernova explosions that scattered stellar debris across light years of space. It was incorporated into the molecular cloud that gave rise to our solar system. It was concentrated in certain minerals by geological processes that operated over billions of years. By the time phosphorus ended up in a form and location where it could be mined and used for agriculture, it had already been through an extraordinarily long and improbable journey. We are not just using phosphorus. We are using the distilled legacy of cosmic evolution, the end product of billions of years of stellar nucleosynthesis and planetary geology. When we mine phosphate rock and spread it on our fields, we are tapping into a reserve that took eons to accumulate. When we let that phosphorus wash into the ocean and settle into deep-sea sediments, we are returning it to a state from which it may not be recovered for millions of years, until plate tectonics brings those sediments back to the surface. In the meantime, the cosmic factories that could theoretically produce more phosphorus are shutting down. The massive stars that forge this element are becoming rarer. The supernova rate is declining. Even if we wanted to wait for the universe to make more phosphorus, the wait would be measured in cosmic time, far beyond any human timescale. This perspective puts our phosphorus crisis in a new light. We are not just depleting a terrestrial resource. We are depleting an inheritance that was billions of years in the making. We are spending down a cosmic endowment that will never be replenished, at least not in any time frame that matters to us. The phosphorus in our bodies, the phosphorus in our food, the phosphorus that sustains all life on Earth, is irreplaceable in the most profound sense. It is star stuff, supernova debris, cosmic treasure, and we are treating it like it's inexhaustible. Let me now turn to a more speculative question, one that connects the Phosphorus story to the search for life elsewhere in the universe. If phosphorus is essential for life, and if phosphorus is rare even by cosmic standards, what does that tell us about the prospects for life on other planets? This is a question that astrobiologists are increasingly taking seriously. The traditional approach to assessing planetary habitability focused on factors like temperature, liquid water, and atmospheric composition. These are important, but they may not be sufficient. A planet could be the right temperature, have abundant water, and possess a protective atmosphere, and still be lifeless if it lacks the chemical building blocks for biology. Phosphorus is one of those building blocks, and its availability may be a limiting factor that we've been neglecting. The concept of a phosphorus bottleneck suggests that life may be much rarer than we've assumed, not because habitable planets are rare, but because phosphorus-rich habitable planets are rare. Even if planets are common, even if water is common, even if the conditions for life are widely satisfied, the actual emergence of life may depend on winning a kind of cosmic lottery, ending up on a planet that happens to have enough phosphorus. Some planets will win that lottery. Many others will not. The galaxy may be full of warm, wet, sterile worlds, planets that would be perfect for life if only they had the necessary chemistry. This idea has implications for the Fermi paradox, the famous question of why we haven't detected evidence of alien civilizations despite the apparent vastness of the galaxy and the billions of years it's had to produce intelligent life. Many solutions to the Fermi paradox have been proposed, ranging from the idea that civilizations inevitably destroy themselves to the possibility that aliens are deliberately avoiding contact with us. The phosphorus bottleneck offers another possibility. Maybe intelligent life is simply much rarer than we've assumed, because the conditions for its emergence are much more stringent than we thought. If phosphorus availability is a limiting factor, then the number of planets capable of producing life might be far smaller than estimates based solely on the abundance of Earth-like planets would suggest. There's also a temporal dimension to this. As we've discussed, the cosmic production of phosphorus has been declining for billions of years. The universe was more phosphorus productive in the past than it is today, and it will be even less productive in the future. This means that the window for life in the universe may be limited, not just by the availability of stars and energy, but by the availability of essential elements like phosphorus. Life that emerges too early in cosmic history would find a universe not yet enriched with heavy elements. Life that emerges too late would find a universe where phosphorus and other essential elements are increasingly diluted and locked away in stellar remnants. There may be a sweet spot, a cosmically privileged era during which conditions are optimal for the emergence of life. We may be living in or near that sweet spot right now. If this is true, it has profound implications for how we think about our place in the universe. We are not just lucky to exist, we are lucky to exist now. A few billion years earlier, and the phosphorus wouldn't have been available. A few billion years later, and it might be too dispersed to support complex chemistry. The fact that we are here contemplating these questions is contingent on the particular moment in cosmic history when we emerged. We are children of a specific era, an era when stars still form, when supernovae still explode, when the elements of life are still being produced and distributed. Future generations of beings, if they exist at all, may look back on our time as a golden age, a period of cosmic abundance that will never return. This brings me to a philosophical reflection on what all of this means. Throughout this documentary, we've been tracing the journey of a single element from its origins in stellar cores to its critical role in the molecules of life. We've seen how phosphorus is forged in nuclear fire, dispersed by cosmic violence, concentrated by geological processes, and ultimately incorporated into living organisms. We've seen how the cosmic production of phosphorus is declining, and how our terrestrial reserves are being depleted. We've seen how the same element that makes life possible is also the element that constrains life's abundance and distribution in the universe. What are we to make of all this? One response is existential dread, a feeling of insignificance in the face of cosmic scales and cosmic constraints. We are tiny creatures on a small planet, dependent on a rare element that the universe is slowly ceasing to produce. Our existence is contingent, fragile, improbable. The universe didn't make phosphorus for us. It made phosphorus through blind physical processes, and we happened to emerge in a time and place where enough of it was available. There's nothing special about us in the cosmic scheme of things. We're just one possible outcome of chemical evolution, an accident of timing and geography. Another response is wonder. The fact that we exist at all, given all the cosmic contingencies involved, is remarkable. Every phosphorus atom in your body was forged in a star that exploded billions of years ago. That atom traveled across interstellar space, was incorporated into the cloud that formed our solar system, became the part of the planet Earth, was weathered out of rock, taken up by organisms, cycled through ecosystems, and eventually ended up in you. You are, quite literally, made of star stuff. Not just in a poetic sense, but in a precise physical sense. The atoms in your body carry the history of the universe within them. You are a product of 13.8 billion years of cosmic evolution, a briefly organized collection of matter that has been around since the beginning of time. A third response is responsibility. If phosphorus is as precious and irreplaceable as this documentary suggests, then we have a moral obligation to use it wisely. We cannot create more phosphorus. We cannot recover phosphorus that has been lost to the deep ocean. We can only conserve what we have, recycle what we use, and ensure that future generations inherit a world where this essential element is still available. The phosphorus crisis is not just an environmental issue or an agricultural issue. It is an intergenerational justice issue. The choices we make today about how we use phosphorus will determine whether our descendants have the resources they need to survive. What would a phosphorus-wise civilization look like? It would close the loop on nutrient cycles, recovering phosphorus from waste streams and returning it to agricultural soils. It would minimize phosphorus runoff by using precision agriculture techniques that apply fertilizer only where and when it's needed. It would reduce food waste, since every kilogram of food that goes uneaten represents phosphorus that was used to grow it. It would shift dietary patterns toward less phosphorus-intensive foods, recognizing that meat production requires far more phosphorus per calorie than plant-based foods. It would develop new technologies for phosphorus extraction and recycling, making it economical to recover phosphorus from low-grade sources. It would treat phosphorus as the strategic resource it is, subject to careful management and international cooperation. None of this is impossible. All of it is within our technological capabilities. The question is whether we have the will to do it. Phosphorus doesn't make headlines the way climate change or plastic pollution does. It's an invisible crisis unfolding slowly beneath the surface of our food system. Most people have never heard of peak phosphorus or the phosphorus cycle. They don't know that the fertilizer that grows their food comes from finite rock deposits that are being rapidly depleted. They don't know that the element in their DNA was forged in a supernova. Raising awareness is the first step toward action. Let me close this documentary by returning to the cosmic perspective one last time. We have seen that phosphorus is essential for life, rare in the universe, declining in production, and being depleted on Earth. We have seen that life is constrained by chemistry, that the universe imposes hard limits on what is possible, and that we are living within those limits whether we acknowledge them or not. We have seen that the story of phosphorus is a story of cosmic contingency, of improbable events and narrow windows, of a universe that makes life possible but not easy. What I want to leave you with is a sense of connection. You are connected to the cosmos in the most intimate way imaginable. The atoms in your body are ancient, far older than the Earth or the Sun, or even the Milky Way in its current form. They were forged in the hearts of massive stars that lived and died before our solar system existed. They were scattered by explosions that briefly outshone entire galaxies. They drifted through interstellar space for millions of years, part of the thin gas between the stars. They were swept up into a collapsing cloud, concentrated by gravity, incorporated into a planet that happened to be the right distance from its star for liquid water to exist. They cycled through that planet's rocks and waters and atmosphere for billions of years, eventually becoming part of a biochemistry so complex and so improbable that we still don't fully understand how it emerged. And now those atoms are you. For a brief moment in cosmic time, those atoms are arranged in a pattern that can think, that can wonder, that can look up at the night sky and ask where it all came from. You are the universe contemplating itself. You are stardust that has learned to ask questions. And the phosphorus in your body, that rare and precious element, is what makes it all possible. Without phosphorus, there would be no DNA to carry genetic information. There would be no ATP to power cellular processes. There would be no membranes to define the boundaries of cells. There would be no you, no me, no life as we know it. Phosphorus is the narrow gate through which all biology must pass, and we passed through it because, by cosmic accident, enough phosphorus was available on this planet at the right time. The universe did not have to work this way. The laws of physics did not have to produce stars massive enough to forge phosphorus. The history of our galaxy did not have to include supernovae that seeded our solar neighborhood with heavy elements. The planet Earth did not have to retain enough phosphorus to support a biosphere. At every step, things could have gone differently. And yet, here we are, products of a chain of events so improbable that it defies comprehension. This is not a reason for despair. It is a reason for gratitude. We exist because the universe, through blind physical processes, happened to produce the conditions for our existence. We are the beneficiaries of cosmic generosity, inheritors of a legacy that we did nothing to earn. The phosphorus in our bodies is a gift from dead stars, delivered across billions of years and billions of light years. We owe our existence to processes that occurred long before Earth existed and will continue long after it's gone. But gratitude comes with responsibility. If we are the beneficiaries of cosmic generosity, we are also the stewards of a cosmic inheritance. The phosphorus that the universe provided is not inexhaustible. The production rate is declining. The terrestrial reserves are being depleted. What we do with this inheritance matters. We can squander it, letting phosphorus wash into the oceans where it will be locked away for millions of years. Or we can conserve it, recycling and recovering and using it wisely, ensuring that future generations can benefit from the same cosmic gift that we received. The choice is ours. The universe has given us everything we need to exist. It has not given us a guarantee that we will continue to exist. That part is up to us. The phosphorus that made us possible can sustain us for a very long time, if we're wise enough to use it well. But if we waste it, if we treat it as inexhaustible when it is anything but, then we will face a reckoning that no amount of technological cleverness can postpone forever. The universe is running out of the element that made life possible. Not today, not tomorrow, but eventually, inevitably, as the massive stars that produce phosphorus become rarer and the supernovae that distribute it become less frequent. We are living in a cosmically privileged era, a time when phosphorus is still being made, when stars still shine, when the conditions for life are about as good as they'll ever be. This privilege is temporary. The window is closing, slowly but inexorably, and we have no power to keep it open. What we do have is the power to make the most of the time we've been given. We can recognize the preciousness of the elements that compose us. We can appreciate the improbability of our existence. We can act as responsible stewards of the cosmic inheritance we've received. We can ensure that the phosphorus which stars created and supernovae scattered, and geological processes concentrated and life incorporated doesn't slip through our fingers. We can be worthy of the universe that made us. That, in the end, is what the phosphorus story teaches us. We are made of rare and precious stuff. Our existence is contingent on cosmic events beyond our control. The universe that produced us is slowly winding down, its ability to make the ingredients of life declining with each passing eon. We are living in a special time, and we should not take it for granted. The phosphorus in your body is a reminder of where you came from and what you're made of. It is a connection to the cosmos, a thread linking you to the hearts of ancient stars. And it is a responsibility, a reminder that what we have is finite, precious, and worth protecting. The story of phosphorus is the story of life itself, from its origins in stellar fire to its uncertain future on a finite planet in a winding down universe. It is a story of abundance and scarcity, of creation and depletion, of cosmic generosity and human responsibility. It is, ultimately, a story about us, about what we are and where we fit in the grand scheme of things. We are phosphorus beings in a phosphorus-limited universe. We are brief arrangements of atoms that were billions of years in the making. We are the universe's way of knowing itself, for a little while, before the atoms disperse and the stars go out and the long silence begins. But that silence is far in the future. For now, the stars still shine. For now, the phosphorus still flows. For now, we are here, alive and aware, able to contemplate our cosmic origins and our terrestrial responsibilities. Let us not waste this moment. Let us not squander this inheritance. Let us be the beings that the universe, through all its improbable processes, made us capable of being: curious, grateful, wise, and determined to make the most of the precious time we've been given. This is the story of phosphorus. This is the story of you. And this is the story of a universe that, despite all its vastness and indifference, somehow managed to produce creatures who could look up at the night sky and wonder. Thank you for watching.